morning, everybody. Let's get started again. Thanks for coming back early. We kicked this day off with 3 keynote speakers. The first one is Tomoki Miyakawa, and he will talk about the diamond experiments and give an overview of those. The floor is yours. I will give you a sign at 15 minutes. And
okay. Can you hear me? Thank you for being here early. I see Christian is missing, but well, never mind. Okay. Okay. Yeah. So today I'll present some recent results from Diamond 2, which is targeted for the winter. And I was told that I shouldn't be sending out propagandas, but I may slip in some slides if I have time. Yeah. Okay. So there was this Diamond Phase 1, very famous. This is the paper by Bjorn Stevens, and we had this number of models plus the real Earth. But in Phase 2, we have more models, actually now 15, depending on how you count it. And this talk was named for, I had my name and Daniel Klock's name, but actually we have a lot of names for each model, so there will be 100 of people contributing for this. Yeah. And the experiment protocol for the Phase 2 was like this. The models were to be set up with a sub 5 kilometer mesh global setup, and the period is 40 days starting from January 20th of 2020, which is the Eureka observation. It's synthesized with the Eureka observation. So we didn't know what kind of circulations would be there beforehand, although we were hoping we would have an MJO in it. The initial state was taken from the ECMWF operational forecast, or ERA5 if it's easier to handle in that model. And the spirit was to don't try to be too precise. It's better to be included with a sloppy setup than try to back up. So many of the models were not heavily tuned, so they could look ugly in some ways, but that's not exactly a bad news because it's really out of the gate kind of models included. So, well, I'll try to follow the way Kathy did in her first very nice talk. And so this, even looking at this first figure, we already see some good and bads. So the good part is pretty obvious. It's the figure is very good looking, and there are a lot of details. I should have put a more zoomed up figure in it. But there is a lot of fine details in each of the models. The bad part is that this is about 1 day after the initial date, if I remember correctly. And there's already a lot of diverse cloud features. It's obviously the radiation needs more tuning. Okay. Oh, so it's repeating what I was saying. So it was both good and bad in a way we expected. And here's the time mean, zonal mean precipitation. And the red line here is from the Diamond 1, Phase 1, targeted for summer. And then the blue here is for the Diamond Phase 2, winter. And these pale lines are the different models. And this blue here is the ensemble mean of these. It's the model mean. And these kind of, forgot the word. These thick colors are the observations. We have multiple observations here, 3 of them, and they differ from each other as well. And what we see here is the precipitation peak to the south of the equator is somewhat shifted to the south compared to the observation. And the small peak here, around 5 degrees north, is a bit overestimated. So we kind of see the shade of the double ITCZ here. But otherwise, it's not that bad for models that are not really heavily trained to be similar to the real world. Okay. So, yeah, I'm just repeating it. Yeah. And then we looked at the diurnal cycle. Here's the diurnal cycle over the tropics, and this is over land. The black is from observation, not really observation, it's era 5 here, but and the colors are the different models. And when you have coarse resolution models, if you don't have cumulus parameterization schemes, if it's coarse, the peak tends to be late. If you have convective parameterizations, you tend to get early peaks. But here, all the models are within 1 hour from this 3 p.m. here. So that's good news. Although the amplitude could be pretty much diverse among the models. And for over the ocean, it's pretty much okay. Not much to see here. Okay. So for the diurnal cycles, we're getting the diurnal cycle peaks, the timing of the peaks are improved in a way we anticipated. Yeah. So that's the good part. And here comes the very ugly part, which is the monsoon. We're looking at the Asian monsoon of the 4th pentab. It's day 16 to 20 average. And so the colors are the 2-meter temperatures, anomaly from the ensemble mean. So in some models, it could be very cold, like 10 degrees colder than the average. And in some models, you can have more than 12 degrees higher than the average. And this model C, I don't really name the models, but for example, in this model C, there's no chance that our skiing resorts would continue their business. See, no snow here at all. Well, so the models have, this could be an issue of a spin up. The models are pretty new, and some of the models don't really have developed a sophisticated way of initializing the land soil moisture yet, and that could be a problem. It could also be a problem by cloud coverage and stuff like that. So that's the ugly part. Okay. So, and we were really looking forward to look at the MJO, and this is the Hofmiller plot, the OLR from the Eureka term, starting from January 20th to February 28th. It's 40 days, and luckily we see some kind of eastward propagation here. However, when we looked at the real-time MJO index, it starts from January 20th here and collapses into the center, and the green is like, it's not really an ideal MJO plot here. But we know that the real-time plot could be contaminated by large-scale circulation. And if we filter it after we have the data after what happens, it could, sometimes we can filter it and get a clean MJO. And that was the case here. So yes, it does look like we had an MJO. It's good. So we decided, and this is from the CPC MJO website. And this, we zoomed up, here I zoomed up into the Eureka 40 days here. So this is basically what we're expecting to have. There's a MJO envelope here. And there are Kelvin waves and Rossby waves intervening into the envelope. So here are the Hofmiller plots from the models, and this one here is the observation. And well, like we could see in the first figure, the cloud covers could be pretty much diverse. But the good news is we kind of see some kind of eastward propagation in most of the models. And, well, so we were looking at the OLR, which could be pretty much dominated by high thin clouds, which were pretty diverse in the models. So we would like to look into things like moisture fields. And if we look into the moisture fields the same way, it's really hard to pick up anything from it if we don't do anything. Because in some models, you see that it's covered by it's quickly covered by high moisture, and sometimes it dries up quickly. So we're seeing the bias kicking in pretty quickly. So first, we'll try to see what the bias is like. And this is a way to see, this is one way to see how the bias is growing. This is a model versus model pattern correlation of column water vapor along the equator. And so the pink plots are model versus model. And the blue plot is model versus year 5. So you see that in the first, which one was it? Oh, this one, yeah. So in the first 20 days, their similarity drops to like 0.4, but the models tend to be similar to each other. Then it is similar the way it is similar to the ER 5. So for some reason, Diamond 2 model tend to be more similar to each other rather than the ER 5, especially after day 20. And if we look at to the actual bias, it looks like this. So we're looking at column water vapor in the color. So the models tend to be drier over the equator, and especially in the Indian Ocean. And it's wetter in the exotropics. And yeah, this grows pretty rapidly. This is an interesting way to find a model that is similar to your model. But I think I'll skip this because I want to reach the propaganda part. Okay, so anyway, we have a pretty strong bias in the OLR and moisture field. So here we subtracted the bias part as a 40-day average, the local average of all the models. So here, now we see the leading edge of the eastward propagating envelope is pretty much similar. The almost invisible black line here is they're all identical for reference, and most of the models have somewhat of the same leading edge here. And if we look at the moisture field, you find these intervening Rossby waves coming in. This is the model ensemble, and it's really hard to pick up whether it's similar or not from here. So I'll narrow it down to the observation and the multi-model mean here. And so this is the OLR. This one is for the column water vapor. And of course, in the multi-model mean, the signals are going to be slightly shifted. So the signals look weak down here, but if, you can see up to about 20 days that the envelope is mostly in the right place. And the intervening westward propagating Rossby waves are pretty much in the right places. Well, if you don't agree, I'll hide the bottom 20 days so that it looks more similar to your eyes. So up to 20 to 25 days, the models are doing a pretty good job. And afterwards, the eastward propagation is unclear in many models after that. Oh, I'll skip this. It's another trick to help make it look more similar, but anyway. Yeah, and the westward signals after 20 days, in the year 5, the Rossby wave signal is smoothly passing through the maritime continent near Indochina and Borneo Island. But for some reason, in many models, I only show 4 here, but in many models, the Rossby waves don't smoothly pass through the maritime continents. It's more like a slow migration, and it's over that near the Borneo and Indochina Peninsula. And I haven't found out why this happens yet. So this is a small summary of Diamond 2 analysis here. So the good thing, the first thing is, of course, it's good looking and highly detailed and good to show to people and fascinate them. But of course, and of course, the timing of the diurnal cycle is good. And the representation of tropical waves and perhaps Mjos during the first 20 to 25 days was pretty good. However, there are lots of things that need improvement. And of course, although it's good looking and the statistics could be very bad, and the clouds need to be tuned to reach a better radiation balance, the monsoon circulations, it's really bad. And we see a dry and wet bias in the tropics and the extratropics, especially in the Indian Ocean, and it's related with the double ITCZ. Some curious points we noticed was that the models are similar with each other rather than with year 5, implying that they're probably making the similar mistakes. And the westward the westward disturbance is slow near the Indochina after 20 days. I'm not really sure what it is, but it could be related with the bias piling up. So I believe I have some time to go into the propaganda part, but I thought it might be good to show our part of the results we did, the Ensemble simulations on Fugaku, because I think Masaki showed how, this is a slide I borrowed from Daisuke, and so Daisuke showed how the Fugaku supercomputer can make a leap for us to go to 3.5 kilometer climate run. Masaki showed how it could bring us to closer to global LES, but no one talked about the Ensemble part, so maybe I'll give a little propaganda talk on it. So this was done for a typhoon event that hit our university campus very badly a couple of years ago. And so we did 100-member ensemble for each initial day, and we selected 16 days to start the simulations. So that's 1,600 members in total. And this is what happens. And so the yellow ones are the typhoons that were initiated in the location we hoped it would. So something similar to the real event. But they didn't approach Japan. And the red ones were the typhoons that actually came close to the real track. So, and I forgot to explain, but this typhoon made landfall on September 8th. And we start the simulations from October 25th to September 4th. So Some of these are more than 2 weeks before the landfall, so it's pretty early for a typhoon prediction. And even so, we got something that looks like a typhoon in the right. Typhoons were generated in the somewhat of a correct place in 90% of the simulations. And although the lead time was pretty long, 55% of the models, the ensemble members, got a typhoon that actually approached Japan. So, which means it's just a single event, but in this case, NICAM could predict that there's a higher probability of a typhoon approaching and by 2 weeks before the actual landfall. So this is the lead time, and the yellow are the percentage of a realistic typhoon being generated, and the red shows the percentage of them actually approaching Japan. So even at August 20th, most of the ensemble members were able to generate a typhoon. After days lead time, almost 100%. And after 12 to 14 days lead time, there was a rise in the models capturing the right tracks that come close to Japan. Okay. So for this typhoon generation part, the key factor was actually this baby vortex, a part of the easterly wave generated from the eastern tropics. And so after August 24th, there was like a ITCZ breakdown kind of event in the eastern tropics, and then these typhoon babies were trapped in the easterly waves, and it approached Japan. So the baby is detectable after around August 23rd or 4th, which was about lead time 16, where the model started to get this genesis nearly 100%. And one thing is that the Japan Meteorological Agency model struggles to maintain this baby. So even if it's in the initial state of their model, they don't really, their forecast doesn't really capture the initiation. But NICAM somehow is able to capture this. And this may be consistent with what Rosmar and Falco was showing. So when they turn on when the cumulus scheme is active, they told me that the easterly waves were much less active, and when it's I don't know, do you call it resolved or not? But well, when it's directly calculated, they get more signals of these easterly waves. So that could be one interesting point to dig into. So, and the other part here is that, so why after lead time 14 did we get the right tracks of the typhoons? So these are the tracks that, this is the PDF of the TCs that actually approached Japan. And this is the one, these are the, this is the PDF from those that didn't approach. And if you look carefully, this black is the actual real typhoon. And you can see that the track is kind of shifted to the north in the ones that approached Japan. and shifted slightly to the south in those that didn't approach. And I won't go into much details, but what happened here was that in these members, there was this upper tropospheric trough that had a northward, I forgot the word, the control, and there was the northward flow associated with the upper level trough that shifted the typhoons northward. So what I want to say is that after lead time 14, the models were able to, the models started to predict this upper tropospheric trough better. And then the typhoons started to approach Japan more. So this is an example of the use of large ensemble, and actually we're not saying it can be applied to all typhoon cases, but it's a demonstration of a case where it could be useful, and it could also be useful to understand why it's why we're able to predict this. So, yeah. And the other one is a large ensemble study on MJOs, and which was done by Daisuke, actually. And so, actually, I should switch to him here if he wants to. But so what he did here was, there was this this MJO event. Actually, there were two MJO events. These were continuous events, right? And so what he did was he did 1,000-member ensemble MJO prediction for these two MJOs. And what is shown here is the timing of when, this is the date of where the MJO is diagnosed to enter phase 7, which is Central Pacific. So when there's 1,000-member of MJOs, they're going to be making mistakes in different ways. So there will be a peak of, peak date where the MJO will reach phase 7. But he found that in some cases there could be double peaks rather than a single peak. And he looked into it and found that in some cases, like this single peak event, it has a strong control that the MJO itself really wants to propagate eastward anyway, so it doesn't really care about other disturbances intervening. But in some MJO events, they're much more unsure that they're propagating eastward, and it could be affected by whether other disturbances affect them or not. So I'll skip this. Well, maybe if you're from, if you were in the high school physics class and were paying attention, maybe you remember this Thomas Young's double slit experiment, where you shoot out one photon, you get some, it reaches some point. But if you shoot a bunch of photons, you start to see wavy kind of structure. And what Daisuke did reminded me of this experiment, because I was paying attention in high school. And yeah. So when we have a large set of ensembles, we start to see the probability distribution, and sometimes a multi-peak kind of distribution in the world. And Daisuke went further to find out why this was, but I might be running out of time. So if you're interested in this, go catch him after this session and yeah, question him. So what I wanted to say here was that this ensemble member increasing dimension is also quite useful. And the good part is it's very easy to apply because it's going to scale. It's just increasing the number of nodes you're going to use, and you're running the same things. So it's easy to scale. And also, if you haven't been associated with this kind of activity, it's a good time to join us because Diamond 2 data is now open and easier to access now. The folks in the DKRZ they're really developing efficient new techniques to share and compare other very strange different data sets. They're already installed in the system and very easy to use. And supercomputers, including our computer Fugaku, and also Pierluigi told us that this Swiss supercomputer is really looking for people who can run interesting scientific experiments. So even if you don't have supercomputers around you, it's now pretty easier to access. And also, we are having this special edition of high performance computing and Diamond or something related with, it doesn't have to be Diamond, it could be NextGems or anything, Warm World, anything. So it's now open, and we have guest editors like Daniel Clark and Pierluigi, Thomas Rakow, Falco back there, and Andres also. So, and this journal is supposed to be very quick in returning reviews. So if you're frustrated in the never returning reviews, it's a good idea to submit here. Yes. Yeah. So yeah, this is just a nice figure I got from Tamaki, who's visiting MPI, and this is very similar to what Kathy showed us in her talk, but this is from the NICAM dataset. So it's an example of how the DKRZ and MPI people are very good at handling other models. They can draw this kind of figure for all of the different models now, I guess. This Toby guy is very bright and doing amazing things. So, yeah. So now we'll be working like this from now on, and we'll be connected, and we'll be using the tools developed by other people and just implementing, and yeah, it would be much easier and much powerful way to proceed. Yes. So please join us if you're, yeah, if you think it's interesting. Thank you.
Thank you, Tomoki. We have time for questions. Please come to the microphones if you have any questions.
If you can show that time series plot of pattern correlations.
Pattern correlations.
As a function of time for all the models.
The busy one, yeah. This one.
Yeah, is that initial fall off in the first 2 weeks, can that be compared with the theoretical ideas of atmospheric chaos Ed Lorenz developed long ago? Is there some prediction of the fall-off rate for a perfect model?
I would love if you could teach me the way, but this fall-off could be very dependent on where we look at. So here we are just looking at this one-dimensional data set over the equator. But if we carry it to the mid-latitudes, we're going to see differently. And so the short answer is I don't know.
But you're saying the data is available. People who are interested could.
Yeah. Yes, please.
Alko, do you want to comment on this point, or? No, just if it's related, then sorry, Tim.
Sure. So Yeah, so I've done some predictability studies using the Lorentzian view, and this is pretty much what we would expect. You see, let's say the blue lines, this is the pattern correlation between observations, so reanalysis, and the models, and they go to about 0 around 20 days. So that's that 3-week. We usually say 2 to 3 weeks because there is some flow dependency, so it's consistent with that. And I want to comment on that with these kilometer scale models, we're not gaining anything in predictability because the atmosphere is a chaotic system, so we're stuck with that 2 to 3 week deterministic predictability limit. And this is consistent with the figure because we go from 1, which is perfect predictability, to essentially 0, there's noise, after 3 weeks. And then I wanted to comment on Tomoki's. I fully agree with, you showed the example of the typhoon, and it's predictable out to essentially 3 weeks, 20 days or so. Yeah. So I think this is one big advantage of these models with explicit convection is tropical prediction. Current models do poorly with waves, and we know the waves are the seeds for hurricanes, tropical cyclones, so that's one where I think there's a big step in predictability and scale in tropical weather prediction. Not only weather, but going out to seasonal, sub-seasonal timescales. And then my last comment on the diamond models, do you have an estimate if the intermodal spread is reduced from, let's say, the CMIP type climate models? We're reducing a lot of the biases, or some of the biases, but is the intermodal spread collapsing?
I haven't really calculated, but by what we're seeing, I don't think so at the point.
That's my guess too. We're still, the intermodal spread is essentially as big as it is with the low-res models, unfortunately.
Yeah, sorry, Tim, go ahead.
No, it's good. I can go offline if need be, but hi, Tim Schneider from NCAR. So, boy, there's so many interesting things to digest, but actually, I think Falco's insight about sort of the fall-off of the initial conditions was insightful. And of course, that's the sub-seasonal, the seasonal forecast challenge. The two comments I was going to make, one is just, I noticed in the last figure you had showing the world map, you know, the comment at the bottom, you probably didn't have time, but just to call out at the very bottom, the comment, you know, you did the visualization straight from the icosahedral grid, which I think I can't remember, there was a conversation, if it was a talk, in your comment, snapshot, directly from original icosahedral data format. That's an important statement. And I can't remember where, but it came up. Anyway, I just thought I'd point it out. The question I have, and this isn't, I mean, this is, you're there, but it's for all of us, right? This is a World Climate Research Program workshop, and we're proposing this within the context of the world, right? And how do we bring, I've been hanging around Peter Van Ovelen too much lately, how do we bring the Global South to these data? Or how do we bring these data to the Global South? This isn't just your problem, right? It's all of our problem, and I think it's an important point as we come together in this forum.
Okay, you mean you want to let the Global South to access the data, or let them calculate their own simulations?
Both.
Okay.
Right. So you have this rich, wonderful, amazing set of data that was largely produced by the developed countries, and we have all these other countries that are just begging for this kind of information and data and tools, and you know it's massive data sets. I mean, when
I have a solution.
Good.
Ask Kathy for a count on DKRZ. That's all. They will send anyone who's interested in. They will give you an account that you can just log in overseas. You can look at the data, use their tools. They can, if they can convince the DKRZ people, they can actually run the models also.
That's good to know.
Yeah.
Thank you.
Rosie.
Hi, your plots about the typhoon heading to Japan versus not heading to Japan reminded me, this summer we were doing a field campaign. Yeah, the next one.
This one.
Forward. Forward. Yeah, that one. So this plot reminded me a lot of the field campaign this summer. You probably are familiar with Tea Park and Tahoe and Precip. We were there to study heavy precipitation, and I noticed that the global models were struggling with the subtropical high, like the models that liked to do the bottom, so take the typhoon straight westward, had the subtropical high extending too far west. And then the models that like to do the top had the subtropical high migrated like to the right,
like being
to the
like
east.
this or like being like this.
Right, yeah. So it's interesting to me because I know you mentioned the trough, which I think is also another possibility, but subtropical highs are very large systems, right? And so we would expect that maybe we can predict them well, but I don't know, maybe there is even a big difference in your ensembles with respect to the subtropical high.
We thought about that and analyzed that, but in this case, it wasn't the position of the subtropical high. It was rather whether the typhoons can get into the course where the subtropical high brings, I mean, whether or not the typhoon gets close to the subtropical high or not was the difference. But
okay.
But our initial guess was that maybe the convection over here could have, in some members, it could have strengthened the subtropical high, and in others, maybe not. So we looked into it, and that was not the case here, but it could be possible in different cases.
Interesting. Thank you. And I like this kind of phenomenological oriented analysis. And I think we should be seeing more of these, not just zonal mean, not just global means, but more like this is the weather that we experience, right? Let's take a look at what it looks like in this model. So I like this.
Thank you.
Kathy?
Yes, thanks. So you had this interesting conclusion that the models are more similar to each other than to era 5, and then your conclusion was all the models do the same mistakes and era 5 is right. So couldn't it be the opposite, that the models are right and era 5 is wrong?
Yeah, I'm secretly searching that possibility, but I didn't want to say it here.
Good luck.
Christian?
Yeah, I have two comments, and they are somewhat related. So your pretty picture plot early on, I counted 15 models. I think there were two that were just two versions of the same model, but, you know, I'm scared. This is expensive stuff. It's difficult to do. And yet here we are already following the bad example of CMIP of building 75 different climate models, many of which are just variants of each other. So I just wanted to put this on note for whoever takes notes. I'm a little worried that we're already, you know, having too many models. There's probably not much you can say about that. But it comes back to this engaging the Global South. I think this idea we dump data and the people in the Global South download it and we give them access to our computers is great. That's not how you collaborate. It's just throwing stuff over the fence. So I think the thought process that's needed is how do we go beyond that, right? And there is a solution, it's just no one likes it. We could have a global center that does this, and several people have proposed this, where the Global South is part of that global center because it's a global center, right? It's not the Americans and the Europeans and the Japanese doing it. We have a place where the globe comes together to do this. And we've never managed to do this. In weather prediction, we have the European Center, so the Europeans have managed to do it. With Destiny, the Europeans are managing to do it again as a European community. But it's you know, people dismiss it too quickly because one of the biggest advantages of having such a center is indeed that we can engage the world in meaningful ways. People can come there, they can work there, they can be there, they can be involved. So we should really, as a community, not be too flippant about this and just start thinking it through. And it's very uncomfortable for each of us because we are involved in efforts that may feel threatened by such an endeavor. And I think I'm not quite sure how to overcome that, but I just again wanted to say that that's true collaboration. And whether that's a real center or virtual center, I don't know. Maybe there's a sort of, in hybrid land these days, maybe there's virtual ways of building such a center rather than building a physical one. I don't know, but it would take some thought. Really don't think that just saying to people, here's the data, just go and analyze it, it's a great first step if it's possible. I will test your suggestion. I will write to Kathy. I'll get myself an account on DKRZ and I'll see how I go.
Rejected.
And we'll see how I go, coming from the south. Oh, by the way, DJF, look at the Australian monsoon, please, as well.
Okay, it's gonna look ugly, but if you're fine with that.
Okay, thank you. We have to move on to the next talk. Steve Yaga, he will talk about staying in high-resolution Earth system prediction, talking about the challenges there.
And just to tell Steve, I'll be your timekeeper because Andreas has to step out for another meeting. So he started you off, and I'll do the discussion at the end.
Thanks, everyone. I'm Steve Yeager from NCAR, not Ping Chang. Ping couldn't make it in person to this conference, and so he asked someone else from the team to deliver this talk in person. So I'll do my best to channel Ping in this talk and share some results from what I think are a really fruitful multi-year collaboration, international collaboration, looking into high-resolution Earth system prediction. Climate prediction. So high resolution here is probably fairly modest resolution by the standards of many in this room, but we're going to be looking at climate timescales in this talk. And as you can see, it involves many people from three institutions, Texas A&M, NCAR, and Chinese collaborators from Qingdao. So the motivating question behind all the work that I'll show is how does ocean mesoscale turbulence impact climate variability, force change, and near-term prediction skill? And the overarching hypothesis that we're working under is that explicit resolution of ocean mesoscale turbulence and associated air-sea interaction significantly improves climate simulation fidelity. And so this hypothesis is based on years of work, and here's one example from a paper by Frank Bryan at NCAR, who did some of the early high-resolution coupled model studies. And what he's showing in this plot is the temporal correlation of small-scale surface wind speed and SST. And what you can see on the upper left is when you have a half-degree atmosphere coupled to a 1-degree ocean, that correlation is negative, which suggests that the SST is primarily driven by the atmospheric winds. But when you increase the ocean resolution to 10th degree, you see this qualitative change in that relationship. So now you have positive correlations over these areas of eddy-rich ocean in the western boundary currents and southern ocean. So this is indicative of the ocean driving the atmosphere. And it's primarily the ocean resolution that matters here, because when you move from half-degree atmosphere to a quarter-degree atmosphere, you don't see much change, maybe a slight increase in the southern ocean. But clearly the move to a 10th degree, an eddy-resolving ocean, is what brings you into better agreement with this observed relationship. And so the tool that we're going to use throughout is the CESM version 1.3. It's the CAM5 spectral element dicore coupled to the POP2 ocean, SICE4, and CLM4. And the choice was made to do all of these experiments with a relatively old version of CESM, because this is a version that had a fairly well-vetted high-resolution configuration. We don't yet have a high-resolution configuration in CESM2. And also CSM2 would be a lot more expensive because it would entail moving to CAM6, which is much more expensive. So to do these experiments, we backported the seam coupler to this older version of CESM. And then we ran experiments in two configurations. High resolution configuration, which is a 1/4 degree atmosphere, 30 levels, top at 3 hectopascal, coupled to a 10th degree ocean, which has 62 vertical levels and no mesoscale, submesoscale, or overflow parameterizations. And that's in contrast to the low resolution configuration, which is nominal 1 degree in both the atmosphere and ocean. The 1 degree ocean does have active mesoscale, submesoscale, and overflow parameterizations. And I just want to note that the details of this low-res configuration will vary depending on the context as I move forward. So we did an enormous amount of computation with the CSM13 configuration. And here's a list of all that we've accomplished in the past 2 to 3 years. So first, we contributed to the high-res MIP project of CMIP6. And there's a couple papers there by Malcolm Roberts that document the results of high-res MIP, and our contributions can be found in those papers. So this entailed a tier 1 experiment, which is just a 65-year AMIP experiment. Tier 2 was fully coupled. It involved running a 1950 control that was drifting, and then a 1950 to 2100 transient simulation that was also drifting, but then you could look at the difference between those two to back out the forced signal. And then Tier 3 was an extension of the AMIP run out to 2050. The big accomplishment was completing a CMIP deck using high resolution, which I think is the first time that's ever been done. Many of these simulations are documented in Chang et al. 2020, which is a James article. This included an 1850 pre-industrial control that was spun up for 650 years at this high resolution, which is the first time that that's ever been done, and that allows you to then look at intrinsic climate variability in a long, stable, coupled simulation. In addition to that, we've completed historical and transient simulations from 1850 to 2100, following the RCP 8.5 forcing scenario of CMIP5. That's a 250-year simulation. And then we added 2 additional ensemble members for a 3-member ensemble spanning 1920 to 2100. We've also done 3 future climate simulations under different RCP forcing scenarios, 2.6, 4.5, and 6.0. We've done a 1% CO2 simulation to look at transient climate sensitivity. That's 150 years. 4 times CO2 simulation to look at equilibrium climate sensitivity, another 150 years. And then 3 ensemble members of AMIP. So that's a complete deck, and that's almost finished. I think the AMIPs are the only ones that are remaining. And finally, the primary focus of this talk will be the decadal prediction ensemble. And to do that, we had to come up with a way to initialize the ocean and sea ice components, which are thought to be the primary sources of memory on decadal timescales. So to do that, we did 5 cycles of a forced ocean sea ice simulation, a FOSSI, that spanned 1958 to 2018. So that's 305 years of coupled ocean sea ice. And finally, we've recently completed 20 ensembles of 5-year, 10-member initialized decadal prediction runs. We intend to complete that set by doubling the number of hindcasts from 20 to 40. And so this is an enormous experiment. As you can see, 2,000 years of coupled CESM at high resolution. So all told, this is over 4,000 simulation years of high resolution climate simulations, has generated over 3 petabytes of data Much of this data is already publicly released. You can find it at this GitHub URL. So it goes without saying there's been an enormous computational challenge to pull this off. We had to port and optimize this version of CESM on machines and try to get a reasonable turnaround in terms of years per day. One machine that we can run on is the Cheyenne platform at the NCAR Wyoming Supercomputing Center. When we run low res on Cheyenne, we get 30 years per day, roughly, and high res is order 1 year per day. To pull off the long pre-industrial control simulation, that was in collaboration with our Chinese colleagues who ran that on their Sunway Taihu Light system in Wuxi, China. And that entailed major code refactoring because this is a multi-core architecture. From what I understand, it's sort of a blend between CPU and GPU. So that took months, if not more than a year, to pull off that recoding. And when that was done, they were able to achieve 3.4 years per day on 65,000 core groups. That's without I/O. When we added I/O, which we wanted, I think we're left with around 2 years per day. So it took more than a year to complete this 600-plus year pre-industrial control. And that porting and some of the issues associated with that is documented in this GMD article by Xiaoxing Zhang. The real success and the way we were able to make hay was when we ported the code to Frontera at the Texas Advanced Computing Center. Our software engineer, Jim Edwards, was able to get really nice scaling that had this sweet spot at 806 nodes, which was roughly 10 years per day on Frontera without I/O. When we added I/O, then we're getting around 6 years per day. So that's certainly adequate to pull off what we were trying to do, particularly since we're running a lot of ensembles. And there's a article that kind of documented that effort on Frontera. The CSM13 code is available, so anyone can take that and run with it. So here's the first results plot. This shows historical and RCP 8.5 runs, global mean surface temperature. These first curves on the top show global mean SST from high resolution in red, low resolution in blue, compared to these observed data products. You can see that the high resolution is in much better agreement with the observations, while low resolution is about a degree too cold. And we see a similar sort of behavior when we look at surface air temperature. So here we're comparing to the GISTEMP v4 data set. The high res is remarkable in terms of its agreement with observations. Both high res and low res show very similar climate sensitivity in terms of global average, but regionally they show very different climate sensitivity, in particular over the Arctic. High res shows much more Arctic amplification that you won't see in this global mean plot. Here's another broad brush result from historical runs, showing a nice improvement in ocean mixed layer depth compared to observations on the left here from Argo drifter floats, we're looking at summertime mixed layer on the top, wintertime mixed layer on the bottom, high res in the middle, low res on the right. What you can see is the high res deepens the mixed layer, which brings it in better agreement with Argo observations, particularly in the tropics and in the Southern Ocean. And I'll highlight in particular improvements in winter mixed layer depth, which is key for ocean ventilation. You can see this very significant improvement in our Southern Ocean deep convection compared to Argo observations. And there's also nice improvement in wintertime convection in the North Atlantic. In the low resolution, we have this common bias of excessive deep convection in the Labrador Sea, and it might be hard to see, but that's deep dark red there in low res, and we've significantly ameliorated that bias in high resolution. And so what this points out is that mixed layer depth is not a 1D process. It is a function of the horizontal processes as well, because these simulations use the same vertical grid and the same vertical mixing parameterization, but we see big improvements when we change the horizontal simulation. And as I mentioned, dramatic improvement in mixed layer depth in the lab C. Now, this was sort of, as I mentioned, a key motivating factor for this entire endeavor was looking for improvements in air-sea interaction and how that changes the climate simulation. So this plot shows point-wise correlations of monthly latent heat flux with SST over this historical time period. On the right are observations. The top panel is the raw correlation, and the sign convention is such that positive indicates or would suggest ocean driving the atmosphere. So when you have a positive SST anomaly, you have positive latent heat flux into the atmosphere, damping of that anomaly. Middle shows the spatial high-pass filter, so you're isolating sort of mesoscale air-sea interaction, and then the bottom panel is low-pass filter, so more large-scale air-sea interaction. What you can see is in the low-res, the agreement is quite poor. It's hard to see here, but these are all negative regions in the low-res, indicating in low resolution the atmosphere is driving the ocean, slave to the atmospheric forcing. And you see very poor correspondence at these small scales. When you go to high resolution, there's just a qualitative difference in this air-sea interaction. So now at small scales, we're seeing a real nice correspondence with observations, this indicating ocean small-scale features doing a lot more driving of the atmosphere than in low-res. And so the overall picture then comes into much better agreement. You can see how this relationship, particularly over these active eddy regions, is much better in high resolution. So this is what we're after, and this is what we achieved. Finally, just showing the SST variance ratio. This is high res over low res. Again, this is raw, high pass filter, low pass filter. You can see much higher small scale SST variance in high resolution because it's an eddying ocean model. We have eddies. This plot shows that we are able to explicitly simulate tropical cyclones in the high resolution to a much better degree than low resolution. So upper left shows global TC tracks from observations, and upper right shows high resolution. So you can see that we're doing a much better job of simulating the genesis and the track of cyclones in high resolution. You can look at the cyclone counts by region, and you can see that high resolution is much better than low resolution. And when you do a composite of TCs, you can see that high resolution gets a much tighter low pressure with stronger winds and stronger TC-related rainfall. Here's a plot showing the improvement in atmospheric rivers in high resolution. The top panel shows the atmospheric river integrated vapor transport from an observed product, and then the atmospheric river related precipitation and observations. And again, you can see that high resolution brings the climate simulation much better agreement with observations for these small scale, high impact atmospheric river events. And when you zoom in on a region like the Northwest here, you can see that the better representation of orography and the better simulation of these river events gives you a much better representation of the influence of atmospheric rivers on the coast, which is what you're after if you're interested in the climate variability of extremes that impact society. This is a plot from the Chang et al. Overview paper of 2020. So the main focus of this talk is the challenge is initialized climate prediction. I'm going to have to speed up a bit, but I wanted to put in this slide just to point out that decadal climate prediction is a challenge even at low resolution. What we're doing in decadal prediction is we are going back to multiple decades into the past and initializing the climate model from some estimate of observations. We don't have good observations this far back, particularly of the ocean, so we have to come up with some way to initialize the model. And then we are initializing ensembles that run out 10 years. These are our hindcasts, and looking at how well we're able to reproduce this observed low-frequency variability, not only of large scale, but it can also be low-frequency variability of weather statistics on climate timescales. So when we did this in low resolution, we produced the CESM1 decadal prediction large ensemble. This had an ensemble size of 40 and had 62 different start dates each November over this time range. It's an enormous experiment, 25,000 simulation years. So this is a challenge even to pull off at low resolution. And there's a lot of outstanding questions. How do you initialize Earth system components that provide memory, namely the ocean, when there are so few observations going back in time? And our solution is to use a forced ocean sea ice simulation. How many members are required to isolate predictable signal variance? That's an open question. But we found that in this system, even 40 members is inadequate for many atmospheric fields due to deficient signal variance in CMIP class systems. This is the so-called signal-to-noise paradox that's been identified. There's predictable variance in the model, but it's weak, and so you need a large ensemble to beat down the noise and isolate that predictable signal variance. I'm going to elaborate on this, so I just want to have a slide to talk about the signal-to-noise paradox. What this is about is the fact that the inherent predictability of Earth's climate is not known. We could think about quantifying that in terms of a ratio of a signal variability over the total variability, signal to total ratio. We'd like to know what that is, but we have no way of knowing it just from observations because we don't know what the signal component is of observed variability. But when initialized forecasts give us a lower bound estimate of that real world predictability, the anomaly correlation coefficient that we can achieve in an initialized system gives us a lower bound of what that S2T ratio is in observation. So we can estimate it from a prediction system. And if we have an ensemble prediction system, then we can easily compute the signal to total variance ratio from that prediction system. And what the signal to noise paradox points out is that if you look at the ratio of the ACC that you're able to achieve with a prediction system divided by the signal to total that's inherent to your model, that can be greater than 1. In other words, the model is able to achieve a prediction skill that is inconsistent with what it thinks its own predictability is. And so when RPC is greater than 1, that's evidence of a signal to noise paradox. And what that means is that you need large ensembles to achieve skill, as I said, to beat down what is excessive model noise. It also implies that there's significant potential to improve and extend predictions by improving coupled model fidelity, and one plausible path forward would be to increase resolution. And I've just highlighted a lot of papers that have come out of the Met Office that have brought the signal to noise paradox into the discussions of initialized prediction. So I'm going to show a few slides on our high-resolution decadal prediction experiment. This is modeled after the CESM decadal prediction large ensemble. Here, this table kind of compares the two systems. The red box is what we argue is the primary difference here. The primary difference is the horizontal resolution of the model components. So we're going from 1 degree to this coupled 10th degree, quarter degree. Obviously, we have a much smaller sample size than DPLE, ensemble size of 10 compared to 40. At this point, we've only completed 18 start dates compared to 64. So I'll be showing results from a 930-year high-resolution prediction experiment. In the spirit of airing dirty laundry, I put this slide in. As I mentioned, we have taken the approach of initializing the ocean using a forced ocean sea ice simulation. When we do that in low resolution, we're able to get a nice agreement with observed upper ocean heat content in the North Atlantic, which is a primary region of high decadal predictability. And this good agreement with observations in our initial condition then translates into good prediction skill in the prediction system in this region. Now, when we did this in high resolution, we were not able to achieve this good agreement with observations in the subpolar North Atlantic. We ran it through 5 cycles, and you can see that in high resolution it tries to warm too early. This mid-90s warming is well documented in the literature, and high res we get this warming kind of in the mid-80s. So this is a flaw in our initial conditions that we knew about, but we decided to proceed anyways. This plot shows drift in terms of global mean surface temperature. The high-res model has a lower drift when you initialize it from realistic conditions because, as I pointed out, it has a lower surface temperature bias. So the blue curves show the high-resolution hindcast ensemble means that tend to track the observations and the forced historical run, whereas when you initialize low-res, we get this drift towards cooler conditions. So that's a nice result, lower drift in high resolution. And now I'm going to go through some map plots of skill. And in these plots, I'll be showing anomaly correlation coefficient on the top, mean square skill score on the bottom. This is a measure of accuracy at getting the magnitude of anomalies. This is more of a linear relationship. And I'm showing results from 40-member DPLE on the far right here, 10-member DPLE, so we're subsampling the 40-member ensemble to look at the 10-member skill. So we have a better apples-to-apples comparison with our 10-member high-res DP. And then I can directly compare high-res DP to DPLE 10 here, and so each point here shows where there's a significant difference. So the open circles means a significant improvement, closed circles means significant degradation. So overall, these patterns of skill look very similar. Much of this skill is coming from external forcing, which is not surprising. But we can nevertheless see regions of significant skill improvement, like here in the Eastern South Pacific in high resolution. And overall, if we look across the globe, 37% of points or of global surface area is improved in high res compared to 20% degraded. So there's, regions of improvement, degradation, but overall, we're seeing an increased skill at high resolution in terms of surface air temperature. Can do the same for precipitation. I'm not going to go into the details in the interest of time. I'm just going to point out that, again, overall, if you compare this map to this map, you see more red. This is a good sign. More red over land. That's really promising. And then the global statistics, again, indicating that this move to high resolution is improving skill. By the way, these are all lead year 1 through 5, so I'm looking at pentadal climate anomalies. And finally, looking at wintertime sea level pressure, which is a quantity that has been looked at in the signal-to-noise paradox literature, so this is certainly of interest. We see this quite dramatic skill improvement in wintertime sea level pressure over much of the globe, particularly in the Eastern Pacific, South Atlantic, and Indian, compared to the 10-member DPLE. Now, this is a field that increasing the ensemble size clearly gives you some benefit. You're able to beat down the noise and get better skill with a 40-member ensemble. But the 10-member high-res DP is on par with or better than a 40-member low-resolution prediction system for this field. So now we can look at these signal-to-noise characteristics. If you look at maps of RPC, this is the ratio of predictable components. Again, greater than 1, indicative of a signal-to-noise paradox. I've switched the columns here, so now DPLE 40 is on the left, high-res DP on the right. What you see in DPLE 40 is that For sea level pressure, which is what this reflects, we have regions of high skill, but these are almost always coincident with high RPC. So we get skill, but it's a signal-to-noise paradox. In high-res DP, we're able to get skill, but the RPC values are much lower. And that's because we have a greater signal-to-total variance fraction over much of the globe compared to DPLE 40. I've summarized that map in terms of this histogram. So now I'm looking at global ACC versus RPC over the entire globe. So these colors indicate fraction of global surface area for high-res DP and DPLE 40. You can just focus your attention on regions where we have ACC greater than 0.5, so regions of high skill. When we get high skill in a low-resolution system, it's almost always coincident with RPC values that are greater than 1. But in high-res DP, we're able to achieve high skill over more of the globe with RPC values that are 1 or less. So we see some amelioration of the signal-to-noise paradox. And what we think is happening, and what we argue, is that mesoscale air-sea interaction facilitates transmission of signal variance from the ocean to the atmosphere. So this is a missing process in low resolution that could be contributing to the signal-to-noise paradox. All right, I'm going to flash a few more results by you. We can do the same thing for other fields. These are maps of ACC relative to these verification data sets from high-res DP, again, for lead year 1 through 5. And the top just shows you whether it's better or worse than low resolution, kind of in a global aggregate sense. So clearly, SAT is better. SST, more of a mixed bag. And in particular, we see this degradation in the North Atlantic compared to low res. And we think that's probably related to the flaws in the initialization in the North Atlantic. So this isn't a completely surprising result that we get lower skill in the North Atlantic. But overall, for all of these fields, for wintertime sea level pressure, upper ocean heat content, zonal wind, SSH, precipitation, we're seeing encouraging signs that moving to eddy resolving resolution improves our climate prediction skill. We can also look at predictability of tropical cyclones now, and we're seeing some encouraging results here. These are courtesy of Dan Fu. On the left, we're looking at TC track density over a 5-year time period. This is the correlation coefficient, and then TC-related rainfall. And on the bottom is from DPLE. So you can see in high resolution, we're clearly getting a much better prediction of TC track density and rainfall, particularly in the northwestern Pacific TC basin here compared to DPLE. If I focus in on this region of the Northwest Pacific and look at time series, this is time series of TC occurrence days. The top time series is lead year 1. The bottom is a 5-year average. You can see that the observed time series is much better represented by high-res DP yielding a correlation of 0.7 compared to 0.4 with low-res, and much better amplitude compared to DPLE, which is very low throughout the time series. And even at lead year 1 through 5, we're able to get a correlation of 0.61 in this region compared to 0.21 in low res. So this is encouraging. We can predict extremes on climate timescales in some regions. And then finally, to end, here's a fresh result looking at multi-year prediction of atmospheric rivers. Again, high-res DP now on the left, DPLE in the middle, and then their difference on the right. And we're highlighting here this region that I already showed where atmospheric rivers impinge on the northwest coast here. We've got high lead year 1 through 3 skill in high-res DP, absence of skill in low-res. So just a significant improvement in our ability to predict atmospheric rivers and associated precipitation in this region. So just to summarize, this international collaboration has facilitated breakthrough climate simulations at eddy-rich ocean, eddy-sensitive atmosphere resolution. We're talking 10-kilometer ocean, 25-kilometer atmosphere. We've completed a multi-centennial pre-industrial simulation, a CMIP deck, and as I've shown, at least a limited initialized decadal prediction hindcast set. These data sets offer excellent opportunity to assess the potential benefits of high-resolution climate modeling. I pointed out ocean bias reduction, SST, mixed layer depth, Atlantic deep water formation. There are others that I didn't have time to show. A key result is that we are achieving this more realistic air-sea interaction with ocean eddies and fronts driving the atmosphere, and we think that that then transmits ocean signals into the atmosphere. We get a better representation of extremes, which is obviously of interest for predicting. And we see this evidence of improved climate prediction skill on S2D timescales. And our working hypothesis is that mesoscale air-sea coupling is a key mechanism involved in transmitting predictable ocean signals to the atmosphere. There are many challenges, too many to list really. Of course, the computational cost. The high-res to low-res cost ratio is about 100. So to complete this 40 start date, high-res DP hindcast set is going to require 400 million core hours, which is significant. This cost then limits our ability to tune the model and to generate high-fidelity initial conditions. Data assimilation remains impractical, and even these forced ocean sea ice simulations, we don't have the experience and the time and the compute resource to iterate the way we do with low-res to refine those initialization data sets. And of course, then we're very limited in the ensemble and sample size that we can achieve for prediction. Validation is a challenge because observational products can be too coarse, both in space and time, so it can be difficult to know if your low skill is because of the model or because of the observations. And I put this as a single bullet point, but data analysis and dissemination is clearly a challenge, and I don't have time to go into it, but one ocean output file at high resolution is about 20 times the size of a similar file from low resolution. That's after we pare down the output. So you can imagine just trying to do climate scale analysis is extremely challenging because we're talking about terabytes of data now that you have to manipulate. And so this it really requires new analysis tools. It requires processing in parallel when you're generating your analyses and plots. And finally, the low-resolution prediction community has clearly shown that skill can be improved through multi-model ensembles, and that's not currently possible. I think we're one of the only groups doing decadal prediction at these resolutions, but there's potential for possible future collaboration internationally, maybe under the auspices of the Decadal Climate Prediction Project of WCRP. So I'm going to end with a plug for the high-resolution modeling workshop that's going to be held in January of next year at the Texas Center for Climate Studies in A&M. So we'll be presenting a lot more of the results from this trilateral collaboration focused on CESM high resolution, but the invitation is open to other interested high-resolution climate models to attend. With that, I'll stop. Thanks.
Thank you. Questions? There's one already.
Yes, very nice talk. One thing that this workshop has done is it has scared me about my regional climate modeling efforts. And I'm wondering how this mesoscale resolution of sea-air interactions may translate into dynamical downscaling where we are prescribing the SSTs. Would you expect this resolution or this variance transmission, as you put it, to kind of be preserved in the high-res regional climate modeling world where SSTs are typically prescribed?
I would think if you're prescribing SST, you're going to err on the side of too much forcing of the atmosphere, but also you're going to be using an observational product that is probably deficient in terms of resolution, because I think the highest SST data sets out there are 1/4 degree, not really resolving the ocean mesoscale. So
Thanks, Steve, for an interesting talk. So I've seen in your earlier DPLE work that you can split the scale in the decadal prediction into a component due to the force response and the internal variability. Just wanting to hear about this split in the high resolution decadal prediction. Is this all coming from the internal variability, or is there also some improvement in the pattern of the forced response?
That's a great question that it's going to be really challenging to answer since we only have a 3-member historical ensemble. It's, questionable whether we can do that same decomposition in high resolution. But the experience from DPLE is for surface air temperature and SST, the external forcing is a dominant driver. But when you look at fields like sea level pressure and precipitation, there's very little externally forced skill. So I'm pretty confident that everything we're seeing in those fields is coming from initialization.
Well, in less than maybe the signal-to-noise paradox is also influencing the sea level pressure response to forced patterns of SST change, and then that could change at high resolution. What do you think about that? If there's also a larger sea level pressure response to forced SST changes.
That's an interesting idea. How would we go about answering that? I'm not sure. With the tools we now have, I mean,
maybe as you say, it's limited by the historical simulations.
Yeah, I mean, I think we might have to wait until we have a larger ensemble of historical and transients. Yeah.
So I have a question. Some of the atmospheric phenomena that you showed, like tropical cyclones and rivers and things, are they the result of higher resolution in the atmosphere, of higher resolution in the ocean, or both?
That's also a very good question. I wish I could hand that question to Ping. But, I suspect that it's both. I think that yeah, with quarter degree, we haven't seen the kind of step change in resolution that would make these phenomena suddenly appear. So I guess my hand-wavy answer is that the ocean resolution is still really critical for those phenomena.
Yeah. Okay. So I just noticed there's this natural constant that no one can explain, and that's the number of cyclones is around about 85 every year, or whatever the number, close in the 80s somewhere, and yours was 111.
Yeah.
So is there some investigation as to why the system makes so many?
I'm sure Dan Fu is looking into that. I don't know how he would answer that question, but I would think there would be some sensitivity to the tracking algorithm, and whether it's appropriate for the model, or whether you need to retune it when you're doing observations versus model.
25 is not that high resolution yet for the atmosphere, right? So
right.
Making so many cyclones is kind of interesting. I'm not trying to bash the model or something. It's really just interesting. Right?
Yeah.
Yeah, Luigi.
First, I think you have some really important results here. So thank you very much. As we try to understand what we should do with our computer time, I think some of your results are really compelling in terms of resolution versus ensemble size. Now, a bit of a naive, in a sense, wanting the world to be a beautiful and simple place. It goes with Christian's question. So we do see strong evidence of these air-sea interactions helping reduce this paradox. Is there a way to design experiments that go beyond what you've already done and try to split out further what the different components of the climate system contribute to predictability? So is there a way, for instance, to say, okay, it looks like the primary one is the ocean. Can we now exclude that? And where is the next best value for money? And it goes back to Kathy's question, should we even bother with the land surface? Is there a value in exploiting those memories? And then next, should we bother with other signals that we think are external, like what's going on in the stratosphere and all that? Is there more value there in trying to assimilate or better simulate processes that currently are a bit outside the envelope? It's a fairly naive question, so feel free to...
It's also a very hard question. I think that one of the rationales for looking at decadal prediction is that we're really interested in the role of the ocean. So, you know, here's a time scale that we know the ocean is going to be important, and if we're interested in quantifying how ocean memory influences the atmosphere, then that's an appropriate framework, initialized decadal prediction. But it's also a very expensive proposition because you have to run these hindcats out to decadal timescales. I think a cheaper framework for exploring a question you asked might be seasonal prediction, right? Where the ocean is still playing a role, atmosphere and land also playing some role, but you know that would be a framework where you could do exactly what you say, which is withhold information from certain components and look at how that changes prediction skill and signal to noise characteristics, and it would be a cheaper way to achieve that. So that's my answer.
Okay, last question, Fang Lin.
If you go back to your slide, the correlation between SST and the latent flux.
Oh, yeah.
That's very striking difference very earlier. And thinking that really because the high variability of SST in local box, like 1 by 1 degree, at high resolution have more like the gradient of SST or SST variance in tandem with atmosphere, or because you're missing a wave model. If you couple the atmosphere ocean both to a wave model, you will have a very beautiful the Charlton number, the softest length will be able to also capture this good correlation between SST and the latent flux.
Are you saying that a low resolution with a wave model?
With a low resolution, if coupled to a wave model, will change your answer there.
You think it would give us this level of agreement with observations just by adding a wave model?
But I was just thinking why you have a better correlation between SST and the latent flux. Maybe it's because you have a local variability, or because you change the change coefficient, the roughly length, you have a higher variability. But in your runs, you don't have a wave model. The wave model is capable of changing this the exchanging coefficient between the atmosphere and the ocean.
Yeah, I don't know if this will answer your question, but Ping gave me this extra slide that I'll show, if I can. So this shows the correlation between, this is similar high-pass filtered correlation between SST and precipitation. So the latent heat flux correlation is really looking at the air-sea interface, how SST and fluxes are related. But this is more getting above the atmospheric boundary layer. It's looking at the relationship between SST and precipitation. And so here we see that, again, over these eddy-rich regions, you see these high correlations in observations that you also see in high resolution, but that are completely absent in low resolution. And so this suggests an influence of SST, into the free atmosphere that I doubt you could achieve with tweaks to roughness or wave parameterization, right? So this suggests that, it really is this persistent, eddy-driven influence on the atmosphere that's important.
Now here's one I would like to see from one of the models that runs resolved convection, because a lot of that is spurious or erroneous relationship between SST and convection, I think, in the tropics there. So
yeah, you
we'll
can see this is completely.
Right. We better break for coffee. I'm getting desperate for a bit of caffeine. I had to get up early for an online session this morning. Thank you, both speakers this morning, and we'll take a coffee break and be back at 11 o'clock. And we'll talk about land ice. Now there's an interesting one.
Okay, thank you for coming back from the break. I hope you had some coffee. We have another session. The first talk will be a keynote talk, and then we have a few contributor talks afterwards. And we will get started with Helen Sarusi, and she will talk about modeling ice sheet in ultra-high resolution, and Helen will be online. Helen, can you hear us?
Absolutely, yeah. Can you hear me?
Yes, well, and we can see your slides.
Perfect. Then let's get started. So
yeah,
hi,
please go ahead.
Everyone. No, was there anything you wanted to add before I get started, or?
Oh, no, you can just get started. Should I give you a note at 15 minutes?
Sure, yes.
Okay.
Absolutely, that'd be great. Thank you. Hi, everyone. Well, thank you very much for having me present and talk to you about modeling ice sheets. I'm sorry I couldn't be here in person, but I had some teaching duties that I could not really escape from. So I wish I had been there with you, but I'm glad I get to talk to you about modeling ice sheet. So I'm Helen Sarusi. I'm a faculty at Dartmouth College. I've been there for just over a year now. And before that, I was working at the Jet Propulsion Lab as a scientist for over 10 years, all this time doing modeling of ice sheets. So first of all, when I talk about modeling ice sheets, I mean modeling the dynamic behavior of ice sheets, so modeling the flow of ice. So yeah, we can move the slide. So this is what, so we have two ice sheets on Earth, Antarctica and Greenland, and that's what they look like from far, far away, from satellite height or something like that. And so this video here shows the flow of ice, so the velocity of ice, and the colors and the scale varies widely between the interior of the ice, where it flows at the rate of like about 2 centimeters per year, and then accelerates as you go towards the coast to reach a speed of up to 10 plus kilometers for the fastest ice streams in Greenland. So this is going around Greenland. So you see the acceleration and the flow of these ice streams and the details that you need to capture as you get towards the coast and you want to capture these narrow fjords. Their width is typically on the order of a few kilometers, 5 to 10 kilometers for many of them. And so that's what we are trying here to capture and model. So that was a view from like far away. Now, if you take a closer look, that's another movie that was done in Jakobshavn, Ilulissat Glacier. That's on the west coast of Greenland. That's one of the fastest flowing glaciers on Earth, reaching up to 15 kilometers per year seasonally. And for the little anecdote, we think that an iceberg from this glacier actually sunk the Titanic. So quite an important glacier. And so this movie shows pictures taken from a fixed position, 1 picture per day for a period of 2 years. And so here again, you see what we've seen in the previous video. We see the flow of ice coming from above on the screen, flowing towards us. So ice is moving. And we have and I hope you can see my mouse here. So we have the front of the glacier here where ice calves, and the boundary between the ice and the fjord can be sometimes a little difficult to see because of all these icebergs and sea ice melange that you have in the fjord. And so here at some point we see that the ice is flowing and the glacier was retreating, so the camera was changed slightly so that we can see continue to see the entire glacier. So that's a view from up close to the glacier, quite different from what we had in the previous video at large scale. So what is it that we're trying to model? Well, we're trying to model all of that, the flow of ice sheets at continental scale. And so let's take a step back and go back just a little bit. So for the longest time, ice flow models have been used mostly to understand the paleoclimate evolution of ice sheets, the alternance between glacier and interglacial cycle. So that's been going on to try to understand the Earth climate. And these models were amazing. They were able to simulate the evolution of ice sheets for like 1.5. This is an example covering a period of 1.5 million years. And you see here on the top the change in the total volume of Antarctica. And so when you look at on the right, you have the sea level equivalent, and you see that these volume change between -5 and almost 15, so like 20 meters overall between glacial and interglacial periods. During the glacial periods, that what Antarctica looks like is what you have here on the left. It extends much further compared to what we're seeing today, all the way to the continental shelf. While during interglacial periods on the right, East Antarctica has retreated a bit, but hasn't changed that much. But most of West Antarctica has completely collapsed, and so there's not much left of West Antarctica. The big Rowney and Ross ice shelves, most of Amundsen Sea sector, if you're familiar with West Antarctica, this is all gone. And so these models were fabulous to do that, but in order to be able to reconstruct like 5 million years glacial interglacial cycles, they needed to have very coarse resolution, at least for a glacier, for an ice sheet model, like 50 kilometers, then you need to have very simplified physics in terms of the equations used to model the flow of ice, very simple parameterizations of a number of physical processes for the ice-ocean interaction, surface mass balance, and so on. So this is wonderful, but when we're talking about modern climate, what is needed, for example, for the IPCC, what's happened over the past few decades or next decades, that you need a completely different kind of models. And so over the past 1 or 2 decades, a number of ice sheet models have been developed to be able to address these specific questions of what happened over the past few decades and what will happen in the next few decades up to a century, so that we can try to improve, for example, projections in the IPCC. A large number of the uncertainty in the sea level projection still comes from ice sheet models, as stated in the previous IPCC report. The largest uncertainties in future sea level and cryosphere change are related to the Greenland and Antarctic ice sheets. Remaining deep uncertainty relates both to ice sheet processes and the atmospheric and oceanic conditions simulated in polar regions. So why is it that we have still these large uncertainties? Well, first of all, ice sheet models are still in their infancy, if I can say so, compared to ocean or atmosphere models. As I said, they were initially used to look at completely different questions that require different skills and different models, and so focusing on the modern climate is something relatively recent. Usually I tend to say that ice sheets are like large-scale system, but talking to this room of people working on like global climate models, atmosphere and oceans, I think maybe it's safe to say that this is a kind of small-scale system compared to ocean or atmosphere, so something slightly different. They of course have complex interactions with the rest of the Earth system, but there are lots of things that we don't understand, lots of physical processes we cannot measure, and we have relatively poor temporal coverage of the ice sheets. We've been having remote sensing observations since the 90s or something like that. So that's almost like 3 decades now. But when you think that ice sheets are responding on the timescales of centuries to millennia or tens of millenniums, that's having 3 decades, it's great, but it's just a really very short timestamp compared to their typical response time. Also, same as something you will have in ocean problems and things like that, there are things we can observe really well. The surface of the ice can be observed relatively easily from space. So we have lots of observations about ice velocity, surface elevation, or things like that. But as soon as you get below the surface, it's really hard to have anything. It's hard to go and measure ocean temperatures at depth. It's even harder to measure ice sheet properties or like basal conditions or things like that buried under like 3 or 4 kilometers of ice. So we have really limited observations about that. Okay, what does it mean what is it that we include in these ice flow models? Well, nothing really different from what you've seen. And this has some similarities with what Martin Lush was talking about yesterday about the sea ice. So ice is treated as an incompressible viscous fluid. You will recognize here the equations that you would have for other components, in a slightly different way because it's ice and it's an incompressible viscous fluid. So the first equation here is your mass conservation that is usually depth integrated. So we simulate changes in the thickness of the ice. And you'll have here like accumulation at the surface and melting at the base. The second is your conservation of energy equation. So we simulate ice temperature. So nothing specific here, advection, diffusion, and internal deformational heat. That's really important. As ice deforms, it's going to warm. That's this last term here. And another thing is that we model ice which is relatively close to its melting point. So we have to include, in some cases, capture the cold temperate transition. And to do that, there are several ways to do that, but the most commonly used is to use enthalpy formulations instead of just temperature formulations, which works well if you have temperate areas with relatively limited water fraction in there. And finally, you have your momentum balance equations. And so here, ice, has like a very low aspect ratio, relatively thin compared to its size. It also flows very slowly. The maximum is like 15 kilometers per year for the fastest glaciers around Greenland. And so all the inertial terms, are negligible. And so we end up with the Stokes flow here. We have our stress tensor and gravity. And this is an incompressible viscous fluid, so we can link the deviatoric stress to the strain rate with this viscosity here, mu, and that mu is taken from the usually adopted law is Glenn's flow law, which is an isotropic law, with B here being the ice hardness, which is temperature dependent, and then you have your epsilon E here, strain rate. So it is a nonlinear equation, but not a bad one. So that's not really a problem. So that's what it goes into these models, just to make sure we're all on the same page. And so we have our ice flow models, and many of you work on climate models, and you know that a few climate models start to include ice sheets, but that's actually not very common, and ice is often treated as something that's not changing. So most of the ice sheet models that are used today are standalone ice sheet models that live just by themselves, kind of disconnected for any climate conditions. So here, I have a list of a number of ice sheet models that were used for the last IPCC projection. This is the list of models that participated to the ice sheet model intercomparison for ISMIP6, which was the main source of information used for ice sheet projections in the IPCC. And so again, lots of different models. They have all kinds of different properties, and we don't need to go into the detail. What matters for us here, as we're talking about high resolution, is what is going on with the resolution of these standalone ice sheet models. So that's for Antarctica again. Numbers would not be very different for Greenland, but we see here the resolution of these models. So you'll see, so those who have just like one number, they usually use regular grids, and the resolution in that case varies between 4 kilo, we have one at 4 kilometers here, all the way to 32 kilometers. You'll see that a number of models have like a range of resolution. For example, this one, the second one, going between 2 and 20 kilometers. So the resolution is, these models don't use a regular grid, but like a grid which can allow to have refinements in places where it is needed, and coarser resolution where in places where having a high resolution is not necessarily very important, such as the middle of the ice sheet where ice flows very slowly, for example. And so what do these models do? So more and more these models use mesh or grid refinement. Here are some examples of that. The most common thing is to use just static refinement. Ice sheets are changing, but the time scale at which there changes is relatively long. So we can just refine using what we know of the velocity today to capture gradients in velocity, refine in areas. For example, this is an example in Greenland. Instead of using a regular grid, we refine where we have these like shear margins, for example, where you have strong gradients velocity. But as soon as, if you use that for a longer period and your ice sheet starts to evolve, ice fronts retreat, velocity changes, ice accelerates, that doesn't work really well because you would have to figure out where you would need to refine. So more and more people are trying to use adaptive refinement. And this is on the right, an example on on a simple idealized case, where refinement happens along the grounding line, so where ice starts detaching from the underlying bedrock and starts floating over the ocean. And so doing that, we are able to refine just where we need. And when these grounding line, for example, moves, we can capture this retreat and continue refining of that along this line. This is an example using a finite element model. This is another example using a finite volume model that has a fixed grid. And in this case, the background grid in this case, I think was like 4 or 8 kilometers. And then each grid is cut into smaller and smaller pieces, and smaller grid cells, so we can refine the grounding line. And so you see where it's darker, it's because you have smaller elements. This goes up to 500 meters. So the background is like 8 kilometers, and the finest grid is 500 meters. And as your grounding line, so the refinement follows the motion of the grounding line. And as the grounding line retreats in this example, the refinement follows that. So we can, so to the first question kind of that I had a bit provocative in my talk, do we need to model ice sheets at 1 kilometer resolution? My answer would be, well, actually, we're actually already doing that. Not everywhere, but in some critical regions that we want to capture accurately, we are already using sub-kilometer resolution to capture these critical areas accurately. Okay. So, what's going on about these grounding line migration? So I just want to spend a few minutes talking a little more about that. Why is it that we need these regions are so critical? So here the grounding line marks the transition from the ice resting over the bedrock to the ice floating over the ocean, and you have a strong change in boundary condition at the base of the ice there, because you go from ice that's flowing over the bedrock, so you have frictional heat. Heat flux is coming from this frictional heat, as well as some geothermal heat flux, to a place where you're floating over the ocean. There's no more frictional heat or resistance at the base, and you have a lot of oceans are relatively warm and melt the ice quite a lot. So a place where you have a lot of melting underneath the ice. So you have really a sharp transition in your boundary condition. And in order to do that, most models actually use what's on the right here, and hydrostatic assumption. So you can use that with any kind of ice model, and you simply look at the hydrostatic condition. So if your ice is thin enough to float over the ocean, it's going to float. And if it's not, then your ice is going to be grounded over the bedrock. And in that area, you need a very high resolution. Let's look at some examples and see what's the resolution dependence on again, an idealized case. So this is like a narrow glacier with like high mountains on the side. And so here you have the bedrock. This figure shows the bottom and the top of the ice, and you have here the floating part, and we see our grounding line here at the transition between the grounded and the floating part of the ice. So it's on the white line that you have here on the bottom plot with the velocity. So again, we have very slow ice motion in the interior and much faster ice as we get towards the front. So we did some experiments with different sliding laws and different melt conditions, so for the grounded ice, and different melt conditions over the floating ice. And here are some examples when in the case where you have relatively large melt conditions. And we look at the convergence with resolution with a mesh varying. So in that case, the mesh is uniform and the resolution varies between 2 kilometers and 125 meters for this example. And another thing is that the grounding line moves continuously. And so how can we track that in our model? So this is one way that we do that. So here on the top, we have the exact grounding line position. And as the grounding line retreats, we want to be able to capture that correctly. However, we have elements or grids that are partially floating and partially grounded. So one way to treat that is to assume that the entire grid cell is grounded, and so there's no melt in there. That's the first example here, no melt. The second one is to assume that on the opposite, like as soon as you have some of your grid cell that is floating, the entire grid cell is floating, and so there is melt applied everywhere. Or you can try to use some sub-element parameterization and calculate the melt as an average, depending on the ratio of the grounded and floating ice, or try to actually capture this transition, in that case with linear just using linear functions, and so capture where the ice is actually grounded or floating. And so we're going to look at the impact of these choice as well as the resolution of our model on the results of some experiments. So here we start from a steady state configuration and start including melt under the floating ice. So ice shelf starts thinning, melting, and the grounding line retreats. And so this is the evolution of the mass, total mass for that system over time, over a 100-year period. And we have two rows with the two different sliding laws. And then we have colors representing the different resolution. And so for the different parameterizations on the left, no melt. The second one is we assume that any partially filled, partially floating cell is completely floating. And then the two sub-element parameterization on the right. And what can we see from that? Well, we can see that the different sliding laws have a slightly different way of responding to the resolution, and that the different parameterization respond drastically differently. The ones that tends to be less dependent on the melt parameterization is the one that on the resolution is the one that has no melt parameterization, so the one on the left. And we can see that even at 125, as we see what's the total volume loss at the end of this experiment after 100 years, we see convergence with increased resolution, of course, but we see that at 125 meters, we are still, we are getting close to something that seems to have converged, but we needed to go below 1 kilometer in order to capture correctly the motion of the grounding line and the correct behavior of that experiment. So this is an idealized, you can tell me like this is an idealized experiment, of course, and I'm just gonna skip that. What's the impact on a real case? So here is the same thing done for a simulation of the Amundsen Sea sector in West Antarctica. So that's this region here in West Antarctica. That's a region that you probably have heard of because it's a region that is changing very rapidly. Today, most of the mass loss in West Antarctica comes from that region, so heavily studied. And here you have the simulation showing the evolution of that region with or without partial melt applied on these grid cells that are partially floating. And this model was done with a resolution of about 1 kilometer. So we can see that depending on how you treat what happens close to the grounding line, you can have a completely different response. On the top, we have some acceleration and thinning of mostly the glacier on the bottom, which is Thwaites Glacier. While on the second case, you have almost like an entire collapse of this entire region with the grounding line retreat and collapse of the glacier going almost all the way to the divide of that glacier. So that shows that what we're seeing on these idealized experiments is something that is even amplified when we look at real case conditions. So that was for grounding line migration, and it showed that we need to have sub-kilometer resolution. Another thing kind of similar is ice front migration and calving. So here's a simulation showing ice front retreat for a glacier in Northeast Greenland. So we have the Northeast ice stream going all the way here, ending up in two different glaciers, 79 North on the top, which is not moving much, as well as Storströmmen, which is experiencing a really large retreat over that simulation that goes to the end of the century. And so first of all, let's take a step back. What is this ice front velocity? So here we want the models want to model the evolution of the ice front position. And so as ice is just simply flowing, the ice front advances if you don't have any calving. But then, of course, you have a retreat due to calving as well as melting along the ice front face. And so these leads to these two terms here that tends to retreat your front position. And so the ice front velocity is simply the difference between these two terms: ice velocity advancing the front and calving and melting retreating it. And in models now, a number of models have started. This is something difficult to include because you need to not just change some conditions, but the entire domain that you're simulating. And so the most common approach for that is to use level set methods that are, and the level set field is like a 2D field that is advected with this ice front velocity. So following this simple advection here. And so that's what we see on this figure, this glacier with the ice front retreating. And I'm going to spare you the same convergence results, but it shows that this also needs to be captured at sub-kilometer resolution if we want to model that accurately. And so we see here this figure, like the fields look relatively smooth and nice. But let's go back to what we saw on the previous slide. So this is not the same glacier, but you get the idea. This is this picture we had of the front of the glacier. So here, this model on the left is already using a sub-kilometer resolution. But do we need like a just paradigm shift and a completely different ways of being able to simulate these front positions and these calving events? Because here we have like very linear continuous model, but reality is a lot more messy than that. We have all these fractures, all these things do we want to model them? Do we need to capture them? That's something people are working on. So I wanted to show another movie. So this, now we completely changing scale. So here we have an idealized ice front that is 800 meters in width. And we're using a very high resolution model that simulates little pieces of ice linked with bonds, and we can simulate the condition of the link between these different little particles of ice that are typically like 1 meter size or something like that, and see how we can, by doing that, we can see how calving events happen and propagate. And so we see here some calving events happening at the front of this glacier. Again, the entire width is 800 meters. And so we can simulate these calving events in great detail. But we need to take a step back again, because how can we link these such high resolution models with something that we want to do at continental scale? So again, this is 800 meters, and the simulation I just showed was running over a period of like just a few seconds, like a minute or something like that. And so how do we go from that to something that you can run for like decades or a century? So that's something people are working on. We don't have good answers for that, but suggest that probably we need to figure out how to go from these micro scale to something much larger. Another thing I wanted to mention and talk about very briefly, and over the 5 or so minutes that maybe I have, is that ice sheets, even though the models are usually not included in climate model, global climate models, and live kind of on their own, they're still not isolated from the rest of the climate system. So they need forcings from the atmosphere, forcing from the ocean. So what do we have for that? So first of all, ice sheet lose mass from 3 main processes: surface melt, which we know from inputs from atmospheric models, as well as calving and ocean melt. So in Greenland, it's about like half of the loss is coming from surface melt. The rest is almost equally divided between calving and ocean melt. Well, in Antarctica is much colder, so there is not much surface melt. And the mass loss comes from about half from calving and the other half from melting from the ocean underneath. So as we're simulating these things, what kind of conditions can we use from climate models? So these 2 figures show the evolution of surface mass balance between kind of now and the end of the century. These are anomalies in surface mass balance. And the idea is not to look at the specific models, but just to look at the kind of input and resolution that we can have, that we are working with and we can have. So these are 2 maps. We can see some anomalies, and we see that there are relatively large scale features that we get from climate models. And many of these regions, for example, here, the Antarctic Peninsula, you have very mountainous regions with very steep changes in topography from one point to the next over a very short distance. Same for the southeast coast of Greenland, for example. You have lots of mountains, very narrow, steep mountains in which glaciers flow. So we need to be able to, and so because the topography changes so rapidly over a very short distance, we need to make sure we can capture the correct conditions on that. And so now a number of climate, so using these relatively coarse resolution, if I can say so, leads to strong limitations for the models. And now a number of climate models are trying to use like class elevations, for example, surface elevation classes, something like that, so that we can have capture that changes a bit better. Same thing when you look at the melt in ice shelf cavities, for example, around Antarctica. So this is one big ice shelf, Werner-Filchner ice shelf, which is, I'm not going to say north because north and south in Antarctica is not quite there. But if you have a map of Antarctica in front of you, that's kind of on the top, let's call that top. And so on the left, we have estimates derived from observations of the melt rate under the ice shelf. And on the right, something that we get typically from a model and that we use for projections. And you can see that the scale is slightly different, but the idea is like, we don't capture any of the details that we see. We're missing all the below zero, so refreezing of that's happening in the big ice shelf. So even if we have the best and perfect ice sheet models that can run at sub-grid kilometer, we need to also work on have forcing conditions that are compatible with this resolution so we can have improved projections. And going to something even more basic than that, as I said at the beginning when I was starting, geometry of the ice, it's really hard to observe anything that's below the surface of the ice sheet. And something as simple as the geometry elevation of the base under the ice sheet remains, at least in some places, relatively unknown. So this is a map of the bed elevation under Antarctica that was published a couple of years ago. And so in some places, there's been lots of observations made. We have lots of details. And again, you can see, for example, the peninsula here. I was telling you steep mountains. That's what we can see here. But there are also regions where we can see on this map where like the bed seems to be really, really smooth. So for example, here, Princess Elizabeth Land, topography seems to be super smooth. And so what's going on there? Well, what's going on is that we just don't have any data for that. So you can see this region here on the right. This map on the right shows all the observations that we have about bedrock elevation under the Antarctic ice sheet. And you have wide, so in some regions, that's relatively good. Don't be fooled too much because like Antarctica is big. So even these tracks that seem to be really close, sometimes they are often at 5 or 10 kilometer spacing between them. But in the East Antarctica, especially, you have entire regions with no measurement for like 50, hundreds of kilometers. So, and a number of studies have shown how critical it is to capture the bedrock elevation and the condition below the ice, because that can triggers unstable retreat and behavior. And so not knowing that is another huge limitation that even if you had the perfect model at the perfect resolution, would be a strong limitation for us. So to summarize that, to the question, do we need to model ice sheets at 1 kilometer resolution? My answer would be yes, we do. Maybe not everywhere, but in some critical regions. And we are actually already doing that. Not everywhere, not for everything, but we are able to start doing that. And we need to go below 1 kilometer, well below that in some cases, to be able to really capture the critical changes and conditions in some key places. Do we need to do even better than that? Do we need to have a paradigm change in the way we model ice with these kind of continuous equations? I would refer you to Martin's talk yesterday about conditions for sea ice. The answer is probably going to be slightly different, but that's something that we need to start thinking about, and at what scale and what exactly we need to model and at what scale. And finally, ice sheets don't live isolated from the rest of the climate system. So we need not only to have models that can be run at this kind of resolution, but also have the right conditions in terms of like the observations we need, what is something as simple as the geometry below the ice, as well as having forcings that we can use that are compatible with these resolutions from atmospheric ocean models and things like that. So I'm going to stop there. And I'm happy to, thanks again for inviting me, and I'm happy to answer any questions. Feel free to reach out even after the talk and after the conference if you want to talk about ice sheet modeling. I'm always really happy to talk about that. Thank you all.
Thank you, Helena. Other questions? Please come forward to the microphones.
Christian's not here, so somebody's got to ask all the questions.
Thanks for stepping in.
Yeah. Hi, Tim Schneider from NCAR. On slide 16, you had the animation of the receding ice front, so there was two glaciers there. There's the one to the left in your image and the one to the right. And I was curious if this is just the way you configured the simulation, or if this is representing a real system where one glacier is receding and the other is not.
The great question. So even though these glaciers are kind of next to each other, and should you think like they have similar atmospheric conditions or things like that, they are, for example, here what is happening is that the ocean conditions in front of them are slightly different. They are in different fjords, for example, and so whether they receive warm or cooler water that reach their front has a strong impact on their behavior. Also, as I was alluding to probably way too rapidly, the bedrock under the ice has a strong impact. So glaciers that are sitting on bedrock below sea level, and that tends to go deeper and deeper as you go inland, will be a lot more unstable than glaciers that are bedrock sloping higher, going higher and higher as you go inland. And so if one has one behavior, has in one case, while the other one is another type of glacier, they would have a completely different behavior, one being unstable, the other one not being a lot more stable. And so that's what's happening in this case. This simulation is using conditions that are exaggerating the warming of the ocean, but the warming was uniform for both of them, and one is responding strongly while the other one seems to have a much more stable behavior, even with relatively warmer conditions. So both ocean conditions reaching the ice front face have an impact, as well as the topography below these two ice streams.
Can I ask one more quick one, Andreas? Do we have time? Because there's another person.
But
so 2 slides later, then you have the simulation of the 800-meter one there. And I'm curious, so in your model, and you may have answered this already earlier in your presentation, but so I would assume that like the tidal levels would have some influence, right? It's more buoyant if the water is higher, and the wave action, because I guess the calving begins due to some weakness within the ice. And so do you model those? Is there a coupling in a sense to the ocean state, tides and winds and waves in these simulations, or is it simply just the dynamics in the ice right now?
So these models, and this data are not my own, I just borrowed that from other people. You can look at this paper if you want more information about that. So in that case, and you're absolutely right that tidal cycles will have a strong impact with tides going up and down and impacting the buoyancy of the ice and all these things. These simulations, however, run over like really, really short period, like a few minutes. So there's no time to have the tides go up and down, but definitely that's something that will impact the stability and can trigger calving, and then things can continue on. But that's definitely something important to consider. I don't think there is much done as of today in most of at least the large scale, like continental scale models for tides. We just take, this is not something that's really, that I have seen being included in these models, worth investigating. Let's not even talk about like, winds and things like that, but just sea level and that changing with tide can have an impact, is detected from some observations in Antarctica, for example. Floating ice shelves go up and down, but not something that I've ever seen being included in a large scale model. So lots of room for improvement there.
Thank you. That was a very nice presentation.
Thank you. Thanks for the questions.
Thanks, Helen. Really nice presentation. I was just wondering, and it's sort of related to this actually, how important is it at the global scale for us to model these particularly these, say, very high resolution calving events, or is it going to come feedback on the large scale, or can we, for example, use more regional refined models in a kind of global regional alliance to actually simulate the kind of important calving events for their impact, rather than as a feedback process on the water cycle or something?
Yeah, great question. So here what's going on is that most of the dynamic mass loss, if I can call it this way, from like glaciers accelerating and contributing to sea level, come from a number of glaciers. So one way is to just focus on these glaciers and see and model them in great detail without having to worry about the continental scale. However, as you go into that's what we're observing today. But however, as you go into the future, you don't know like where things will start changing, and when you are able to bring like warmer waters close to the front of Greenland glaciers or within ice shelf cavities in Antarctica, these glaciers start to respond to that. And so then once you start these processes, you trigger large changes. And so if you're interested in like just like a few decades, glaciers behave relatively independently. Like if you go back to the beginning, like you look at Greenland, if I go back there quickly, and we can go like somewhere here, like they are relatively defined glaciers close to the front. They have their own catchment. But then as you go towards longer and longer periods, these different glaciers can interact. And that's something that was seen also in some of the Antarctic videos later, like the different catchment basins start to interact with each other. So what if you remove most of the ice in one area, it's going to start impacting the other regions around that. So yes, so depending on the timescale you're interested in, you can look at just regional and like individual glaciers. But as soon as you start going into longer periods, that starts to be a problem, and you need to include the feedback between the different regions.
Thank you.
Sure.
Any other questions? I had one. How important is the ocean resolution then for your ice sheet modeling? Like if you have this very localized processes happening, the current climate models like the CMIP models have very coarse resolution ocean models. Would a high resolution ocean model be very beneficial here?
Yes, so having high resolution ocean models or having a way to get the detailed patterns of melt under Antarctic ice shelves, or like what happens in the fjords. So all these fjords around Greenland, being able to capture that is really key, because where the melt, so first of all, like for example, the fjords, can we have warm enough conditions so that that's going to impact and melt the front of glaciers and start to initiate triggering mechanism that will lead to the calving of the glacier is key. Also in Antarctica, lots of ice shelves are not, some are really wide, some are not that big, like just like a few 50 kilometers wide or something like that. And so having just like when models are like 10 kilometer, let's say something like that, you cannot really capture any circulation really well in these cavities. And how much melt, so that's going to impact how much melt water, but also where the melt happens is really key, because if you start melting close to your grounding line, you are thinning directly close to that. And so your ice is melting and your grounding line is going to start retreating again and again, and that might trigger again some instabilities. While if the melt is happening close to the front, where the buttressing is not so important, and that's going to have a much lower impact and not impact the glaciers as much. So it's not just like the total melt that matters, but how it's distributed below your ice shelf that matters. So being able to have climate models that do resolve these cavities and with the best possible resolution is something that is critical for us in able to have good forcings, because this is really one of the key triggering mechanisms for the stability of these ice shelves and ice streams. So that's something really, really important.
So would the ideal resolution of the ocean be the same as the ice sheet model then, or can you get away with coarser?
It doesn't have to be the same, but just being able to resolve, and you'll know more, people doing oceanography will know more exactly what needs to be captured, but being able to capture the circulation in these ice shelf cavities is something really critical. So maybe I'm advocating for my own field, obviously, but for me, like having climate models that can resolve these cavities and have circulation that's good enough to resolve that is something that really would be critical to have in the next generations. And I know a number of models are working towards that. It's not obviously not something easy to do, otherwise it would have been done already, but that's something that is critical.
Thank you so much, Helene, for being with us and for answering the question, for a great talk. We have to move on to our next speaker.
Thank you all. Thanks for having me, and don't hesitate if you have more questions coming down. I'm always happy to talk about that. Thank you.
Thanks. So this section is now contributor talk, so those will be 15 minutes long. I will give you a 2-minute warning Can you say something? I think we cannot hear you.
Silvina, your mic is muted. Could you unmute in Zoom? Silvina, your mic is muted.
Yeah, I know.
Okay, we can hear
I'm
you
lost. Yeah, I lost my control of the Zoom thing. So anyway, I'm ready now. So thank you for letting me using this time slot to put the Cortex perspective on this ultra high resolution modeling. This presentation has been prepared together with Daniela Jacob from Cortex co-chair and Irene Lacke as well. So let me just remind all of you, most of you know what Cortex is. You know that the Cortex vision is to advance and coordinate the science and application of regional climate downscaling through global partnerships. And Cortex, it's an activity within WCRP that has been running for almost 10 years now. And it includes the whole land areas of the world divided into 14 domains today. And in those 14 domains, regions, those are regions for which the regional downscaling is taking place, and when we have an official Cortex designation. So these are the domains that most of you already know. And several groups around the world have been providing and performing simulations under coordinated protocols for climate impact studies mostly, and understanding climate responses to global change of these regions. And there is a striking feature of this coordinated activity is that the Cortex model outputs is available online through different platforms, the Earth System Grid Federation and Copernicus Climate Data Store by now. And this is open access, standardized, quality control. I mean, there is a large support on the products already available from these activities. And just to mention, Cortex now is an instrumental part of the new WCRP core project, Regional Information for Society, so we still around there. You know that when talking about the ultra-high resolution simulations, from the Cortex perspective, and you already share this view, we are trying to go from the global vision of the system towards the very local scale. So we are trying to connect this global climate modeling with the regional climate modeling, which has been typically run for Cortex in the range of 12 to 25 kilometers. That's the standard resolution. And now we are understanding that we have, since these coordinated experiments, we could have the possibility to understand the uncertainty in the simulations for the present and future scenarios of different areas of the world. And now we understand that we need to improve that and go into high resolution. So going to high resolution has been initially proposed within the Cortex umbrella through these flagship pilot studies. These flagship pilot studies are frontier research topics, which not only include very high resolution and convection permitting modeling, but also other frontier research topic that fit within the Cortex interest. For instance, climate changing, urban areas, aerosol, and the distillation of climate information, of course. And so I would like to draw your attention on which has been the flagship pilot studies that have been working on modeling at ultra high resolution. That are quite a few. These flagship pilot studies started in 2016, more or less. So some of them are close to finish. but you will see that we have learned some interesting lessons from these initial results. So all these, let me put emphasis on this. These are coordinated efforts on modeling at ultra high resolution. So what I would like to share with you is the main outcomes of those coordinated efforts and the lessons learned. As you see in this map, here you can see the cortex domains, and in red, these are the subdomains in which coordinated efforts in modeling at ultra high resolution have been made. And this is what I want to show today. So there are one flagship pilot study centered on the Lake Victoria, a couple of activities in Europe using high resolution modeling and more than modeling. I will comment that later. There is one activity in Central Asia, East Asia, on the third pole environment area, and another on the southeastern South America. Several of them sharing the interest on analyzing extreme events, extreme precipitation events, but some of them have already started looking at other components of the systems. So let me just show some examples of results achieved so far. This is the activity on the Lake Victorian Basin, which main objectives, one of the main objectives is to assess the added value of high resolution. The added value of these very high resolution simulations is something that you all already know, and there are plenty of studies that have demonstrated that high resolution, convection permitting resolution simulations improve the representation of a number of characteristics of mainly precipitation. And these are not different from those, but let me jump in another result that I think it's very, very interesting related to the next one. But concerning this flagship pilot study, they are a consortium of 19 members from 10 different countries, running a number of models at convection permitting resolution and with the parameterization on. So they compared the two sets of simulations with a number of regional models. And they found, I'm not going to go through the details of the figures, but I'd like to mention the main outcomes. They found, as everywhere, improved timing of the diurnal cycle of precipitation, reduced bias in a number of raining events per year. This is the bias in the parameterized ensemble mean, and this is the bias in the convection permitting ensemble mean. So it's a clear reduce in the bias, without unanimous improvement nor deterioration in other features like the spatial distribution of total rainfall at the seasonal cycle. But they found some substantial biases in other variables, such as the top of the atmosphere upward radiative fluxes. Concerning the second flagship pilot study, the one focused on the Alpine region, actually, again, the research topics highlighted are the added value of this modeling at convection permitting and the evaluation of uncertainties. And here is where I would like to draw your attention, because this is the largest coordinated effort at modeling with convection permitting models. They performed simulations with 20 models using models at 12 kilometers and also at kilometer scale resolution, and perform present climate and future scenarios. So the most interesting outcomes that I'd like to share with you is that if you look at the, for instance, the precipitation uncertainty at the daily or hourly basis, in red you can see the box plots for the convection permitting, the 3 kilometers ensemble, and in blue, the 12 kilometers ensemble. And this is just for a region in Italy, and here you have the bias of the daily precipitation, and here is the bias of the hourly precipitation. So you can see that in general, they found for this region smaller biases in the convection permitting at the hourly time scale. And the interesting feature is that the uncertainties in the convection permittings at the hourly scale is really smaller compared with those in the 12 kilometers runs. For the climate change signals, these are for intensity, frequency, and heavy precipitation. And these are the different regions in which the changes are evaluated. Again, red 3 kilometers, blue 12 kilometers. And overall, what we see here is that the spread of the boxes, the uncertainty in these climate change signals for hourly precipitation change in terms of intensity, frequency, and heavy precipitation is always smaller for the convection permitting simulations compared with that of the parametricized convection experiments. And finally, moving out from the precipitation lens, for future heat waves, they also evaluate the change in the temperature, the mean temperature of heat waves, and find in these examples that the high resolution modeling ensemble produces a larger response. This is the high resolution and this is the low resolution, so it's a higher response. But also the uncertainty, this is the spread, is smaller in the high resolution. So moving to another example of these activities, I have 2 minutes left, I guess. For the third pole environment, the East Asia domain. Again, this is a consortium with 25 international research groups from 12 countries with 7 regional climate models, and perform some specific case studies, short-term simulations, and year-long simulations. Then they have a different publications in which you can find some specific results. But what I would like to highlight is that they understand, these groups understand that it was impossible for a single actor to perform such a huge number of simulations, more than 90 simulations at 4 kilometers, without a coordination effort. And they also realized that they could be able to create links with larger programs within the third pole environment. And the important thing is they collaborated with the data center to make the simulations available to researchers outside the project. And this is something that Cordex usually pursues all the time. Try to summarize here another example focused on South America, Southeastern South America. This is the region where extreme events are very, very frequent and very interesting. And in this flagship pilot study, an interinstitutional collaboration, intercomparison among different convection permitting simulations, and also integration with the ESD community, the statistical downscaling community, to find a common information about. Yeah.
2 more minutes.
Okay, thank you. To find, I was saying, to deliver useful information for the impact of climate change on hydrology in the region. So though this is much more modest than the other ones, it includes 5 convection permitting models with case study and a couple of simulations of different lengths. And they also found, to summarize, that the convection permitted simulations improve the quality of the precipitation-related metrics, mainly on extreme and means, and displayed a variety of performance. And let me just finish with this. This is related not specifically with the simulation using convection permitted modeling, but with the data that you need to provide the models to run convection permitted models. And the data is related with the distribution of land use, land cover change. And this flagship pilot study is focused on land use, land cover change. And what is made here is to provide ultra high resolution at 0.018 degree for the Eurocortex domain and show how is the impact of that high resolution land use, like land climate change in the simulations. I'm not going to go through the details of this, so let me just make the summary here to avoid taking too long. But they really show that the impacts of land use change driving modification of small scale soil, vegetation, and snow patterns on atmospheric processes and local conditions. So we have to have in mind that it's not only the modeling component, but also the inputs that we need to provide to those models in which we have to pay attention. This is to finalize. We all know parameterized convection is one of the major contributions to uncertainty in climate projections. We need improving observations, model development, and process understanding together with increased resolution that can help in reducing this uncertainty. And we are finding that the uncertainty is substantially reduced in this ultra high resolution simulation. That is a good news. And finally, I want to emphasize the importance of interinstitutional collaboration and coordinating science as key aspects to address this end-to-end study. So thank you very much for your attention, and sorry if I took more time than I was allowed to. Thank you.
Thank you, Silvina. We have to move on. I'm sorry. Thank you again for joining us and for giving a nice talk. Our next speaker will be Peter Lauritzen from NCAR, and he will talk about the coupling of MPAS atmosphere with CAM.
So this says do not use. Okay, I'll use. There we go. So I would like to provide a perspective from the factory floor where models are being put together. So in other words, where we couple up dynamical cores with physics packages, or we put new parameterizations into existing physics packages. I'm trying to convince you here in this talk here that this is an important science problem rather than a software engineering exercise where science is not really involved. And we're a bigger group here that are trying to emphasize this point. We wrote a very long paper that just got published, and some of the people here are in the room, where we discuss these things of these thermodynamic and energetic consistencies or inconsistencies that I'll be talking about here. If I lose you, please go to that paper if you would like to read up on it. Apologies for the long title here, but this is a project where we've been pulling in the MPAS dynamical core into the CAM physics package, and I'd like to make you aware of some of the things we have to think through to do that in a somewhat energetic and thermodynamic consistent way. So to motivate the problem, I'm going to talk mostly about the CAM physics package because that's the one I know best, but I think this applies to other physics packages as well. So they're typically hydrostatic. They usually use a pressure coordinate that in a hydrostatic approximation becomes a mass coordinate. And it assumes that pressure stays constant during physics updates. That's quite convenient because then enthalpy is conserved. In the density of pressure, physics packages typically only include dry air and water vapor, so there's no condensates in there. And if these physics packages are being used in coupled climate modeling, usually we try to have a closed total energy budget. That does not mean we close the energy budget rigorously from first principles. It just means that we're closing the budget, and we're often using fixers to do that. In terms of dynamical cores, a lot of the really high resolution quote-unquote weather dynamical cores are developed with a z vertical coordinate, not a pressure vertical coordinate, so it's a constant volume coordinate. They're obviously non-hydrostatic if you're down at the 1 kilometer scale. They include condensates in the pressure field, also known as condensate loading, so those are really big terms when you go to high resolution. And they typically also use a different discrete prognostic state compared to the physics package. So the question is, how do we couple those two and maintain some level of thermodynamic and energetic consistency? So we have some issues from first principles. If you take the Navier-Stokes equations and you derive what total energy should they conserve, then you get different formulas depending on what your assumptions are. So if you use a constant volume model, which is equation 35 here, you can derive the equation that the time tendency of the global integral of kinetic energy. If I can point with this here. Yeah, K is kinetic energy. Then you have the CVT term, that's the internal energy, and then phi is the geopotential energy. That's conserved assuming Z is constant at the model top, which is the case for MPAS. When you derive these equations with a pressure coordinate, that means the model top is constant pressure. That means it's not constant in Z. Then you get this extra term here, which is a work done by pressure at the model top. So we're conserving different energies in physics and dynamics here. I'd just like to highlight non-hydrostatic, hydrostatic. These equations here do not change. It's only that the kinetic energy will have a vertical component if you're non-hydrostatic, but otherwise they're the same. The other issue is the condensate loading. So you can write out the energy equation assuming no sources and sink, as shown here, where you end up with a loop of all forms or all components of moist air. So here you would be looping over dry air and water vapor with these terms here if you were in the CAM physics package, whereas MPAS would include all the condensates. In the case of CAM, it's cloud liquid, ice, rain, snow, grapple, and you can add more if you wish to do so. So that again leads to two energy formulas. Apologies for showing low resolution results here. This is results from a 1 degree simulation, but I tried to estimate, how much energy is there in non-precipitating condensates in a global climate run. So this is the energy imbalance induced by that in a run with CAM. And as you can see, it's really low. The global average is below 0.01 watts per meter squared. So it's pretty small in the grand scheme of things. However, locally, this effect will obviously increase. Another issue from first principles, usually if you run, for example, a convection scheme, it will produce a heating rate, and you need to convert that to a temperature change. If you do that under constant pressure and constant volume assumptions, you get different results. So in the constant volume case, which would be MPAS here, you can think of a piston where the piston here stays fixed. Then your temperature will increase proportional to the heat capacity at constant volume, whereas in the constant pressure case where the piston here would move when you add heat, then the enthalpy is conserved and your temperature increment is scaled with the heat capacity under constant pressure. So that leads to different time tendencies. So a little word of warning when designing these physics parameterization interfaces, it's really dangerous to carry a temperature tendency because you don't know under what assumption it was applied. Then there's a discretization issue. This is a particular example for MPAS. So the prognostic variables for MPAS is modified potential temperature, the theta here, the velocity components are orthogonal to the cell faces. Rho here is the dry density, and then the heights, which in MPAS do not move. And then you have mixing ratio on a dry basis. I denote that M. And then the physics package uses temperature, lat long velocity, pressure, and then it has mixing ratios based either on a moist or a dry basis. So one issue that can happen here is, I just told you Z stays constant in pressure, whereas in the CAM physics package, you hydrostatically diagnose what the height should be based on temperature and pressure and humidity. And if you just use whatever code is sitting in CAM, you get a discrepancy as shown down here. Again, apologies, it's 1 degree, it's 1 year average, but it shows you that for level 31 here, which is at 400 meters, and level 21, which is about 10 kilometers, and at 25 kilometers, the difference between the MPAS height, which is what comes from the dicor, and then your one you diagnosed, if we just used our framework as is, that can differ by quite a bit, 5 meters to like 48 meters. So that means the physics would be seeing the wrong heights if you're not careful. So I won't go into the detail of how we work with the equation of state, hydrostatic balance, and so on to achieve some level of consistency. I'm just going to list what consistency we're able to enforce. So first of all, what I just talked about, we cleverly were able to select mid-level pressure so that CAM physics diagnoses the same height as an MPAS. That's what I illustrate here. Now the differences are 0. The energy increments in physics, we make sure they're applied in MPAS on the constant volume assumption. There you also have to be a little bit careful how you convert your temperature tendencies into the potential temperature tendencies. And closely related to that, we then made sure that the energy increment that physics sees under constant pressure assumption is the same as the energy increment seen in the MPAS dynamical core. And then third, but not lastly, the physics package has an energy fixer, and that's based on constant pressure assumption. So we have to make sure that when that fixes spurious energy errors from the dicor, that they use the correct energy equation. I'd like to highlight some other first principle issues that resolution won't fix for you that I think are important. This one relates to the specific heats. I alluded to that earlier, but a lot of newer dynamical cores, such as FV3 and the spectral element dynamical core, we assumed the latent heats are functions of temperature. And if you do that, you end up with this energy equation here, where when you sum over all components of air, you use the appropriate heat capacity. So you use the appropriate one for dynamics, or for dry air, water vapor, and liquid and ice, whereas most physics packages use only the one for dry air. And we computed the discrepancy between these two a little while ago, and it's actually 0.5 watt per meter squared. And just for your reference, the climate signal we're looking for is 0.1 watts per meter squared. The other issue is, and again, I'm speaking from the point of view of CAM here, I don't know of anybody who actually does that, but if you look at the energy equation and you write the full energy equation out with the flux terms on the right-hand side, I won't have time to go into all of the details here, but there's one term here which is the enthalpy of evaporation and falling hydrometeors, and usually that's not included in the energy equation. And that happens to be the biggest term for closing the energy budget. So that's illustrated on this slide here. So this is the energy imbalance of CAM physics. When you run the parameterization suite, it's about 0.3 watts per meter squared. This is what these flux terms that were not included look like, and you have to make up temperature at the surface. I just use the temperature as the lowest surface level. But by eye, you can see they basically look the same, and if you subtract them, you see that we close the energy budget in many regions to within 1-2 watts per meter squared, and before the imbalance was about 30 watts per meter squared. Again, 1 degree resolution, 1 year average here. So obviously, if you look on the daily time scale, these terms are much larger. The other thing is, I'm sorry it gets very technical here, but when we import parameterizations, they may make assumptions that are not consistent with the host model. So we conserve enthalpy, which leads to the energy conservation in pressure coordinates. We've been importing this boundary layer scheme called club, and that's based on preserving a thermodynamic variable. However, that does not conserve the same energy as the host model, and that's what we've illustrated on this plot here. So the imbalance in terms of energy budgets between CAM and club is about 0.4 watts per meter squared. So again, these inconsistencies lead to pretty large errors. And we obviously fix all of them with all kinds of clever fixers. Last slide, then I'm done. Also like you to be aware that the dynamical core is a big source of non-conservation. At 1 degree, they conserve between 0.3 and 1 watts per meter squared. Fortunately, that's a problem that slowly goes away as you increase resolution, but you have to do it in both dimensions. So from pure convergence, your energy dissipation of the dicore goes down. So I would assume that a lot of these 1 kilometer models here have pretty good energy conservation, or at least I hope so. With that, I'll take questions.
Thank you very much, Peter.
For now by Dick Linzen, consistent something resolution in the horizontal and the vertical. He was doing it from the standpoint of linear wave theory, but is that still worth looking at?
Yeah, I believe it's important to preserve that aspect ratio. So yes. So I saw it in running. We've been doing quote-unquote high-resolution 25-kilometer runs with the same number of layers as the 1 degree model, and the horizontal energy errors go down, but the vertical ones are the same as 1 degree, meaning your energy conservation is still pretty high, or non-conservation is high. So yeah.
Thank you very much. Yeah, the energy in the Z model is very different to the P model, so good point. So, yeah, how do you think that the more accurate formulation of the thermodynamics, for example, the latent heat and the specific heat dependence on temperature is not negligible for high resolution model, I think. What's your view on this?
Yeah, so in that paper, we tried to estimate the errors associated with that. And it's again the same energy imbalances that we saw before, like 0.5 to 1 watt per meter squared, but locally a lot larger. The only problem with that approach is when you want to specify the enthalpy flux at the surface. Now you're weighting liquid with the correct heat capacity, which if I remember correctly is 3 or 4 times larger than that in dry air. So that means if you're off with that temperature at which water leaves the atmosphere, then your errors go up.
So you suggest temperature dependency on latent heat, temperature dependency should be included in? Okay.
Yes, I believe so, especially when you're going to higher and higher resolution.
Yeah. In that case, yeah, I have a existing meteorological textbook based on constant latent heat. So very different energy formulation balance. So we are very puzzling for comparing other references. So
yeah.
Thank you, Peter. We have to move on to the next speaker, which is Anesh Subramanian. He will talk about data assimilation for climate. And sorry if you didn't see this on your agenda, we had to move the talk from Anesh from tomorrow to today. So we will gain a quarter hour at 15 minutes tomorrow. Sorry? But we lose them today, so it's a zero-sum game.
Great. Yeah, thank you for the opportunity to speak here. I'll be wearing two hats for today's talk. One, the Digital Earth's Lighthouse activity, where we are trying to lead an effort on data assimilation needs for climate prediction and attribution. So I'll give a summary of the outcomes from a workshop that we held in May here at NCAR at the MESA lab. And then the final 3 slides will be more on research results that I'm part of in terms of high resolution data assimilation as well as modeling. So the workshop was organized by Patrick Heimbach, Sergey Frolov, myself, Andrew Gettelman here at NCAR, and Nico from WCRP helped a lot with the logistics. The motivation for the workshop was to bring together a community of modelers, data assimilation experts, as well as observationalists who think about the climate problem. Most of the data assimilation focus currently is on the weather or weather to subseasonal timescale. Very little has been done in terms of climate prediction, climate reanalysis. So how do we bring a community together for this? And the goal was to think about what can be done in the next 5 to 10 years to move this forward. The effort came under 2 lighthouse activities in WCRP. One was the explaining and predicting Earth system change. Patrick was a part of that, and then Digital Earths, which I'm part of, and this current workshop on ultra-high resolution is also part of the Digital Earths effort. We are trying to bring together different parts of WCRP that is interested in data assimilation, especially for climate. So within the explaining and predicting Earth system change, there are 2 working groups that have interest and relevance to data assimilation. One is observing and modeling the Earth system change, and the other is integrated attribution, prediction, and projection. Within our Lighthouse activity on Digital Earths, there is an entire theme on data assimilation for climate models, as well as the Earth System Modeling and Observations ESMO core project, which was presented on the first day on Monday about. There's a big theme on data assimilation there as well. So bringing all these interests together, we organized this workshop with goals to motivate the need for data assimilation in the climate community, to develop capabilities for data assimilation in climate modeling, identify opportunities that help transfer advances in current DA tools that have been developed for weather, to move that into climate research as well, and then a discussion on the structure for the next community-driven climate DA development teams. And we wanted to engage across a broad section of the community, modelers, data assimilation, as well as observations relevant to climate prediction. The main themes that we organized the workshop on, we identified these 5 main themes. One was initialization and calibration for prediction and reconstruction. So here we were thinking from seasonal, interannual, decadal, and longer time scale, how do we initialize our climate projections and climate predictions? How do we calibrate them? A second theme was reconciling climatology of observation-constrained reanalysis and free-running models. How do we compare the mean state? How do we reconcile the climatology? A third one was closing budgets and representing trends in reanalysis. Current day reanalysis is built from weather data assimilation, where weather data assimilation cycles are stitched together largely. They don't necessarily close budgets. They don't necessarily represent trends accurately. How do we improve upon that? A fourth theme was uncertainty in the mean state as well as the trend, thinking about ensembles and other ways to represent uncertainty in reanalysis products. There's some movement in this currently with current generation reanalysis bringing out ensemble reanalysis as well. And the fifth theme was on reducing model error in climate projection and reanalysis modes by confronting models with observations using the DA formalism. How do we identify model errors? How do we represent them better, potentially with stochastic parameterization or other ways to represent model error? The scope was to, one, build a community for climate data assimilation coordinated by WCRP, new ways for focused DA development relevant for climate prediction specifically, not weather timescales, but longer timescales, thinking about the whole Earth system. And like I mentioned here, by climate, we mean seasonal, intraannual, decadal, and longer timescales. The topics that were discussed included data assimilation for climate prediction, reanalysis for climate attribution, climate model improvements within a data assimilation framework, and then observation-constrained data sets to look at budgets and closed budgets, like what Peter mentioned also in the previous talk. So some of the outcomes from this workshop, we are working on a report that will help assess existing scientific knowledge on data assimilation for climate prediction, determine gaps in current methodology and capabilities, identify next steps to improve data assimilation for climate prediction, make recommendations for future directions, as well as exploit interagency within countries as well as international collaboration for this effort. Some specific needs and opportunities that were identified at this workshop. One was to develop climate models with DA systems from the get-go. Currently, it's a bit of a patchwork, but we think that if data assimilation systems like Ensemble, either Ensemble Kalman filter or, if possible, adjoint, which was discussed but harder to do in a fully coupled Earth system, if those can be developed when you develop the climate model itself, that can help identify biases in the DA framework, help identify model error, looking at analysis increments or other aspects of DA, as well as it can help initialization of climate prediction by producing better initial conditions and reducing shock by using reanalysis from a different model, rather build initial conditions directly from the climate model that you're using itself. So that was one outcome. The second one was a fully coupled data assimilation is a desired thing for coupled Earth system prediction. Some groups, especially on the weather and subseasonal timescale, medium range, are developing this, like ECMWF. But we think even for climate prediction, this is something that will really help, but there's scientific development that needs to be done in terms of understanding the coupled transition layers better, in terms of initializing them better and identifying errors better across different components. So for this, towards this, we need better observations across this transition layer. Currently, there are very few co-located observations of, for instance, the atmospheric boundary layer and the ocean boundary layer, or sea ice and ocean boundary layers. So we need better observations across the transition layers to understand covariances across these components. We also need to use existing climate observations better, such as all-sky cloud data that currently is not assimilated well enough, as well as long-term ocean profiles such as Argo. It's used for ocean reanalysis, but not in a fully coupled framework. That needs to be exploited more. We also need more long-term sustained observations of Earth system to build better climate reanalysis as well as climate DA products. We need reanalysis that is specifically designed for climate applications that have closed budgets in them, that conserve climate properties, as well as online model error correction was discussed, where model errors can be identified using analysis increments within a climate model framework. This is something that needs to be developed more. It's ongoing effort here in NOAA as well as at ECMWF. So WCRP can facilitate collaboration on many of these efforts, especially bringing reanalysis centers and climate modeling centers together. So now I'll switch to the science part of the talk. I'll quickly present a couple of results. One is this regional high-resolution model that we have been working on in collaboration with Ibrahim Hotayet's group at KAUST, NCAR, DART, and folks at Scripps. We are running a 4-kilometer ocean model coupled to an 8-kilometer or a 16-kilometer atmospheric model with the ESMF Neopsy. We have a DART as the data assimilation setup within this. And we have run uncoupled and coupled data assimilation. Just a quick highlight result from this. We have run 4 different setups of uncoupled ocean model only versus a coupled ocean and atmosphere model. The key takeaway message that we have seen from these results is that the coupled model with model error with perturbed physics has reduced error both in the forecast as well as analysis. And then one quick result from another study that I'm part of. Chris Hill will talk about these runs more. This is the Mjos Echo coupled model nature run, which has 6-kilometer atmosphere, 4-kilometer ocean resolution. The model has been run for more than a year now. Danny Du, who's a graduate student, has been looking at MJOs in these model runs, and we have identified a few MJO events that propagate past the maritime continent. The next step is to do process diagnostics to understand land-ocean atmosphere interactions over the maritime continent in this high-resolution model to understand what helps the MJO propagate past the maritime continent. So with that, I'll end the talk. I'll take questions. Thank you. And sorry for shifting gears, but hopefully.
It was great. Thank you. Questions?
So Anish, one of the things that wasn't on your list of things to do was develop new techniques. Does that imply that the current techniques for data assimilation are suitable at high resolution? I'm a bit worried because the divergent component of the wind field is a much bigger player at high resolution, even in the exotropics, right? It always is in the tropics. And we know that data assimilation systems do not represent divergent component of the wind easily with the current techniques. So has there been some discussion on we need completely new techniques for data assimilation, and where does that live in your shopping list?
I would think that would live, it's not fully coupled data assimilation, but there is scientific development that's needed towards high resolution. We didn't discuss a lot about resolution of climate models and what needs to be done for higher resolution climate modeling. But I would think that would come under the fully coupled data assimilation development also, that we need better methods, scientific methods. There was some discussion about combining machine learning with traditional DA methods, because machine learning is cheaper if you can train it, where you can assimilate higher resolution observations into high resolution models. Whereas traditional methods, like either ensembles, you need 2 large ensembles, or adjoint linearity is a problem when you go to higher resolution. So that was discussed. Yeah.
Thank you.
Thank you.
I had a question as well. Like many observational data sets are inhomogeneous as well, especially if you look at satellites or radio sounds. Did you talk about this as well? Like if you assimilate inconsistent or inhomogeneous observational records, you will also basically have an erroneous trend, isn't it?
Yeah. In terms of trend, yes. Like if you have inconsistent trend, which is why we need longer term climate records. Currently it's dealt with by either super obs, where you assimilate observations within a subgrid by smoothing it and making it match the model resolution. But yeah, if you have inconsistent time records in terms of observations, that's an error in your trend, but I would assume that can be built into the error covariances or like the error that goes into your DA framework, right? Yeah, great question. Thanks.
Thanks, Anish. Then no further questions. We move on. Thank you again to the last speaker of the session, which is Benjamin Hillman, and he will talk about radiation code in ultra-high resolution models.
Don't use that one, it says. Okay, great. Hello, everybody. I'd like to start by thanking the organizers for giving me the opportunity to speak today, especially about something that's so very obviously more computational science than physical science. So, and I also realize I'm standing between everybody and lunch, so I'll try to keep this kind of a broad overview. So I'm Ben Hillman from San Diego National Laboratories, and this is work that I've been doing with collaborators on the E3SM project to bring, let's think of it as overcoming one of the computational challenges to running ultra-high resolution models on sort of next-gen supercomputers. And in particular, that's this radiation code that we've developed based on RRTM-GP that we're using in multiple versions of ultra-high resolution simulations within E3SM. I'd like to call out especially Matt Norman, who did a lot of the porting work on this, including the backend. So let's get going. Obligatory acknowledgements. We did this under the Energy Exascale Earth System Model Project funded by the Department of Energy, and also the Exascale Computing Project, which aims to bring an exascale ecosystem to the Department of Energy to leverage new hardware. And the simulations I'm going to be showing were done on the Summit supercomputer, which is at Oak Ridge Leadership Computing Facility. So to call back to Aaron's talk from yesterday about high-resolution modeling in E3SM, and also define some terms that I might mention throughout this talk and ground everybody, we have two main approaches to high-resolution modeling in the Department of Energy. The first, which Aaron talked about yesterday, is EMXX and SCREAM. So EMXX is this complete rewrite or new version of the atmosphere component of E3SM, and C++ using a performance portability framework to allow it to work on a variety of new machines. And SCREAM is a particular configuration of that model which targets 3-kilometer resolution globally. And Aaron showed some results from that yesterday, and this figure below here is the cover image from the James article, which describes the 4chan version of that model, and we're working on starting simulations with the C++ version of that model kind of as we speak. The other is this E3SM MMF. I'm not going to talk too much about this, but this is our version of E3SM that implements the multi-scale modeling framework, which of course Dave Randall pioneered back in 2 decades ago now, I think. And a recent paper from Walter Hanna et al. Documents our implementation of this. So we're actually using this new radiation code in both of these configurations of E3SM. And I said this wasn't going to be a science talk, but I wanted to show a pretty picture anyways for a number of reasons. One, so this is outgoing long-wave radiation simulated from a short debug simulation that we did recently with the new C++ code at 3 kilometers, so demonstrates that the radiation code actually works, which is nice. And also, Aaron wasn't able to include these pretty pictures in his presentation yesterday, so I wanted to include them somewhere. And also, as a little bit of a sales pitch, this was created by Chris Durai, one of our collaborators, using this new tool, NCViz, which Paul Ulrich developed. And this is actually a native grid plot on the unstructured CubeSphere spectral element mesh. And it can do native grid plots very quickly, and so yeah, it's pretty nice to have that capability. That's kind of non-trivial, I think. Of course, these simulations come with a cost. These things are incredibly expensive. This is a graphic that Aaron showed yesterday, which shows the relative costs of the different processes in the new EMXX C++ atmosphere model. Of course, the dynamics dominates the model cost. But radiative transfer is no slouch either, and taking quite a few core hours as well. And so we want to speed that up as much as possible. This is all run on the GPU on Summit with 3,072 nodes of Summit, I believe. So this is already showing kind of the accelerated version of the code that we've been able to produce by porting this over to use a performance portability framework. So you might be asking, why do we need yet another radiative transfer package? The field of radiative transfer is very mature. We know that we can get the right answer given the right inputs to very high precision if we have enough computer time. The answer is really that the new computers that are available to us to do these very high resolution simulations, especially in the Department of Energy, are all leveraging GPU accelerators for the majority of their computational power. And our current climate codes, including the radiative transfer, will simply not run on those new architectures without a lot of work, and in fact need a lot of refactoring to even be able to be ported to those new computers a lot of times. Robert Pincus and others have already done a lot of the work for us in writing the RRTM-GP radiative transfer package. So this is a rewrite of the popular RRTM-G radiative transfer package. Apologize for the permutation of acronyms here. We just keep adding letters onto the end of this thing. And that rewrite was to expose more parallelism in the radiative transfer code to allow it to be ported to different GPU accelerators. And we actually worked with Robert and started the OpenACC port of that code. So it's written in Fortran with OpenACC directives targeting NVIDIA GPUs. And now there's also OpenMP directives added to that code. And there's a fork of that code which I believe is working on a set of CUDA kernels for it as well for NVIDIA machines. This is great, and it gives really good performance on NVIDIA GPUs. But one disadvantage of this approach is that porting additional backends, you have to kind of like add directives to the code, and that's in kind of the user or developer-facing portions of the code. So to ensure that we could run on new machines, so we're targeting new DOE machines, which are not all using NVIDIA GPUs. There's Intel GPUs and AMD GPUs. And so to ensure that we could run on day one when those new machines come out, we made the decision to, again, rewrite this code, this time using a C++ performance portability framework. I'll explain what that is in a minute here. But the idea here is that we can take advantage of excellent vendor support for C++, and have a robust C-based API, which has a very good chance of being able to work on day one. Another nice thing about it is it enables single source portability to new architectures. And what this means is that the radiation code itself can stay unchanged when we go to new machines, and all that needs to change or be ported is the backends that we use. So Aaron talked a little bit about the COCOS performance portability framework. This is actually using a different performance portability framework called the yet another kernel launcher, YACL. Matt Norman is famous for his acronyms, I think. And so this is actually a pretty small C++ library in comparison to COCOS with only about 5,000 lines of core code. So if you just want to use simple arrays and use the pool allocator that it provides, it's actually a pretty small effort to do that. The emphasis is on simple and readable syntax with minimal developer concerns. One nice feature is that it allows kind of Fortran-like look and behavior in the resulting C++ code, and I'll show an example of that in just a minute. There's a growing library of Fortran intrinsic functions, so if you program in Fortran, you'll see things like size and max val and min val and things like that kind of look familiar. And it has a pool allocator, which is efficient for automatic allocation of YACL objects. This is nice if you need to do frequent allocations and deallocations at runtime. And the main draw is that it runs on CPUs, currently CPU threads with OpenMP, NVIDIA GPUs with CUDA backend, AMD GPUs with a HIP backend, and Intel GPUs with the Cycle backend. So I know showing like equations in talks is perilous, and probably showing code is even more perilous, but I wanted to show a super simple example of what this looks like just to demonstrate its use. So this is a really simple kernel that you might run into, and this is pulled actually from the RRTM-GP and RRTM-GP-XX source code. And all this is doing is just adding two numbers together, basically optical. It's incrementing an optical depth. And so there's a loop over quadrature points, over the number of layers, and over the number of columns. In order to port this to different GPU backends, I wanted to note here, this sort of also demonstrates our porting strategy with our RTM-GP in general. And that's that we have very tightly nested loops. And that's so that we can have, you see that we've exposed as much parallelism as possible here. We have the number of quadrature points, which is order of hundreds, number of layers, which in Scream is 72 or 128, and the number of columns. So this kernel will be pretty large in terms of computational size, but it's small in terms of the amount of code that exists in this kernel. And that kind of gives the compiler a chance to optimize it and to do the right thing. We found that if your kernels get too big, then you can kind of run into troubles depending on compilers. So to port this using directives-based backends, you can see that we have directives for both OpenACC and OpenMP. The details aren't super important here, just that you have to kind of embed both of these things into the code. And then I'm showing below here the exact same kernel that's rewritten in C++, but using the YACL performance portability framework. And so this loop is just replaced with this parallel for construct. It's very simple. The actual computation that happens inside of that kernel looks almost identical to what you would see in the Fortran code. And so this is kind of to show you that it's okay to use C++ and it's not that scary. I'm going to show very quickly some performance results. So this is showing performance in our RTM GPXX standalone. And it's just showing this is a single node of Summit and varying the amount of workload for the problem. And so the x-axis here is columns per node, and the y-axis is runtime. And a couple things to note. Obviously, you get a lot better performance by utilizing the GPUs on Summit, and that's because Summit was designed with a lot more GPU power than CPU power. The blue curve is the GPU curve with the C++ code, and then there's a number of other CPU codes that are shown here as well. One is our C++ port of our RTMGP, that's in the yellow. The green and the red is the F90, two different F90 versions. And so you can see that we get comparable performance in the C++ port to the original F90 versions, which ran very well in the CPU. Some details on integration in Emacs and Scream, just really briefly. We did have to write a new interface layer between the Emacs or Scream driver and RTM GPXX, with different objects that we need to kind of port between the Emacs infrastructure and the RTM GPXX code. Let's say that these two different performance portability libraries are 100% compatible, but we had different layouts between the two, so we had to do a little bit of data copying, which ends up being pretty inexpensive in this case. And this is also an example of the fact that you can use different frameworks for GPU porting within the same code base, I think, which is nice. And I'm not going to say anything more about that. And then the last result that I want to show is just some scaling on Summit in a recent, I think the same simulation or same type of simulation that I showed at the start of this, which is Emacs or Scream on Summit at 3 kilometers. And this is showing the runtime versus the number of nodes. And so we've been able to run this out to 3,072 nodes of Summit. It scales okay, but not perfectly. And we have some ideas about why that might be. So I'm actually going to skip the summary and just put up my references here. And I'd be happy to take any questions. I know we're pushing up against lunch, so happy to talk during the lunch break too. So thanks.
Benjamin, we have it's time for 1 or 2 quick questions.
Really nice talk. You said they're compatible and you can use both Cocos and YACL. Can you just give a bit more rationale for why you chose not to use Cocos and you choose YACL?
Yeah, so this was actually developed specifically for the MMF version of E3SM, which does not have any YACL in it. So we had already ported the CRM that's used in that using YACL. And one of the main motivations to that is that YACL provides kind of a one-to-one Fortran porting, so you don't have to completely restructure the code in order to do this. The thing ends up looking very, very similarly, as opposed to if you're writing things from scratch, you're willing to go through and do a whole bunch of refactoring of the code anyways. You can go to zero-based indexing, you can rearrange the data order. You don't have to do all of that with YACL. So it was a faster way of getting to something that worked for us and was portable than going through the process of converting it to looking like C++ and Cocos.
Last question.
Going a little bit of a science question, but not completely. So I imagine that even with your performance improvement here, your radiation chunk of the bar plot's still going to be pretty big. I wondered if you have any plans to take advantage of RRTM GPs flexibility in running a spectrally less dense or a less dense spectral grid, reducing the number of G points tuned for your particular application?
Yeah, we already are actually. So we were originally running with the 224 and 256, somewhere in there. And then we're using the set of absorption coefficients with the reduced number of quadrature points that Robert developed, I think, as part of the machine learning strategy that they had. Yeah.
Okay, let's thank all the speakers from the morning session again. Now is a lunch break, an hour long, so we won't reconvene in here, but you will directly go into your breakout sessions afterwards at 1:45 p.m. So enjoy your lunch. We're meeting back in here at 3 for report back from the breakouts.
sample modeling and also some kilometer scale ocean modeling that kind of led into this. And I'm starting off showing an obligatory, dubious movie, because everybody likes those. So this is something from I shot on my phone back in 2015, I think, or maybe 2014, when we were visiting NASA Range, where we'd just done the global kilometer scale ocean run. And this is some of Martin Losch's ice algorithms. And we were just blown away by how this kind of looked. We didn't realize that our models could look like that. So, but this is also, it's a group of people. So I've just got a lot of names of people involved in what I'm going to talk about. So precursor work is what I thought I'd talk about a tiny bit first. So this is ocean-only work. And just, people have talked about cases for kilometer scale activities. Two examples at the top there that I kind of always talk about. One is work we did back in the late 90s around deep convection in the ocean, and there's a process where kind of convectively homogenized water gets capped off. I just fondly remember that work. Nothing worked until we got down to a kilometer scale, and then all of a sudden this narrow layer of fluid that in the real world caps these things off started working. And so that was an eye-opener even back in like the 90s, although it was a tiny model, obviously. And then some work by Tom Hain with looking at the Denmark Strait overflow. Similarly, if you talk to Tom and when he looks at these things, you just couldn't get anything that really convinced observationalists that you had anything credible until you got down to like a kilometer scale in the ocean. So those were kind of messages we got way back subliminally in the 90s. Then sometime around 2014, we did decide to do some global 1 to 2 kilometer ocean things. There's a picture of me back in 2014 with Dimitri and Martin and Bela Fox-Kemper, and this is when we were talking to people about these runs. And these, again, with the two things that we put into that were kind of interesting was tides, some sort of adaptive closure for the subgrid scale things you still don't resolve, and then also saving the full model state every hour. And I'm going to say this over and over again because it was just kind of interesting to us how it worked, and making it sort of available. It actually led to about 100 or more analysis papers so far. It's been very heavily used, this thing, especially around kind of features that might be detected by satellites. So we work a lot with NASA. And in fact, I was saying to someone today that it's kind of interesting because these calculations we did back in 2014 have featured a lot in planning for this surface water and ocean topography mission, which actually launches on December the 5th this year. And so, 6 months from now, we'll find out whether anything we concluded from the models actually has relevance to the real world. So we hope we'll see. But some general lessons from that ocean-only work were really a couple of things that I think we do feel, there's a bunch of us who feel that kilometer scale global ocean stuff does have some weird Turing test passing qualities. And in fact, at Ocean Sciences this spring, we even had a little online Turing test that is still there. You can go there, and it just asks you to try and guess which, various fields it shows, which one's real, which one's from a model. And we found that the distribution is totally random. People can't tell. So now we carefully selected the things to doing that. But also the things we learned from this were just archiving and sharing the model state at high temporal and full spatial resolution can catalyze enormous use. So it's good for analysis. It's also good for identifying problems and things. And then I would say the other thing is just leveraging synergies with observational plans is super important because the models are getting ahead of the observation, so we need to kind of keep focused on that. So the thing I wanted to kind of connect with this community more around, and I should say I'm super excited to see how many people are doing this stuff. I didn't realize that so many people were actually doing these sort of things, is coupled work that's sort of built on that. We work a lot with NASA Goddard. So in the last 5 years, we've started doing some coupled work with them using their Mjos atmosphere and land model at about 6 to 7 kilometers horizontal grid with 72 levels, has aerosols and aerosol cloud stuff. And then on the ocean side, we actually have coarsened slightly just for kind of the first pass of this to get computationally tractable stuff. And we did this actually, this was part of a Diamond 2 experiment, but then we extended it out for 14 months. So in the Diamond websites and things, some of the output from this experiment is there. And then we just decided, well, let's carry on from, the 40 days all the way through to April 2021. So I was going to say a little bit about some of the things we've been doing with that. But first, with that, we've also done this heavy emphasis on ways to kind of share high-frequency, time-dependent, full-resolution fields widely. And it's already getting quite a bit of use both for science analysis and also as kind of, again, this sort of nature run for thinking about mission planning in the NASA community. So just a couple of obligatory slides about, what sorts of things we've saved. So you can see we've saved hourly instantaneous 3D fields of a lot of different quantities, velocities, pressures, humidities of various sorts, cloud cover things, CO2, and so on, 15-minute kind of things not saved at key levels. And this is all in the atmosphere, and then a bunch of diagnostic terms, so cross correlations of terms and things that, but again at hourly frequencies throughout. And so this is a huge amount of stuff. It's like petabytes of numbers, and a lot of people are like, "You sure you want to do that?" And we feel it's actually at least worth experimenting doing this. And then the same on the ocean side. So we say hourly prognostic and diagnostic fields on the native grid again, so kind of 2 to 4 kilometers over the planet with 90 levels. And these are, the ocean is actually a lot simpler than the atmosphere, so there's a few velocity fields, some ice things, but not a lot of the ocean. We don't have any biology or chemistry in this ocean setup. And so then just wanted to say a little bit about sort of where and how we've been sharing everything, because we've been also experimenting with that. And then I'll show some of sort of the things we've been doing to look at some of the solutions. But we do a lot of our computations at NASA Ames, so our kind of master archive of stuff is at NASA Ames, and I say it's about 5 petabytes of kind of a mix of NetCDF and some binary format we should be ashamed of, but it worked well for performance reasons, and now we're living with it for now. But the NASA Ames group have actually done some fun things, like they have more than 500 kind of pre-computed MP4s of all those fields that come out, looking at them in various perspectives, and so you can actually just go and browse through the thing remarkably easily, and it's kind of, at least, I find it kind of useful for just getting a feel for how the solution looks. So the thing on the right there, all those little icons are kind of all the little movie click-ons, at least for the atmosphere. I think there's a whole bunch for the ocean as well, so I just kind of, and they're all just kind of there that people can look at. Then the other thing so NASA Ames is a secure facility. They have some networks that they can share things publicly over, but the performance is not great. So we've also been doing some stuff with Johns Hopkins and something called the Open Storage Network. And there we've done a subset of things, but we have been looking at using kind of nice Python stacks, Dusk, FSspec, ZAR, ZFP compression, so all the things people have been talking about. And we've also been working with hardware groups around something called the Open Storage Network that NSF does, that actually is sort of quite a promising thing for offering kind of open access to data significantly below commercial cloud storage and with no direct egress. So that's still a bit of an experiment, but I think it's kind of been promising. So some actual examples of things that come out of this. Here's one that is looking at SST and atmospheric cold fronts. So on the right there, you can see some turbulent fluxes and some sea surface temperature plots. This is in a paper about kind of, how cold fronts behave over ocean patches. And so one of the things that sort of we've written in this paper is about just the fact that where you have the right combination of a cold front moving over some cold water to some warm water, you get this interesting deepening of the planetary boundary layer that actually enhances latent heat fluxes. And so, there are actual physics things that you can see in these coupled runs that, they're fairly high frequency and they're very high spatial frequency, so both temporal and spatial frequencies. Then wind work from the ocean on smaller scales is another thing we've been looking at. So this is taking the wind stress and the currents and just calculating, the momentum exchanges from the offline from these hourly saved states. We actually find that the total kind of amount of wind work is actually significantly larger than previous modeling studies have reported. This is an example of something where we're kind of doing this, again, in this sort of nature run, trying to guide mission planning. So NASA has a bunch, and ESA as well has a bunch of missions around wind wave kind of phenomena and satellite mission planning. So this is something that, again, is kind of providing useful information for that sort of work. And then Finally, this is just one that is slightly interesting in the sense that what we did discover is in these higher resolution runs, we use a traditional kind of vertical mixing scheme, called the K-profile parameterization. And actually, it's parameterizing things that are now more resolved than we expected. And so when we start comparing this with profiling observations from McLean profilers off Hawaii, we find, you can see on the right there's kind of some spectral plots, but what we find is actually we're kind of over mixing things and damping down variability that's more than we should because we had this parameterization on. So one lesson we're learning from that is, and some interesting questions is really, that was a place where in the kilometer scale we really needed to kind of revisit that. And so that's our kind of current coupled thing that's out there. We're actually planning to move towards a higher resolution thing on the basis that 1 to 2 kilometers is where we think the sweet spot is for the ocean. It's kind of where the high latitude deformation radius and ocean sub-mesoscales kind of come together at high latitudes, such that the sorts of processes that you want to see resolved in the ocean work. So we're starting a 3 to 4 kilometer atmosphere, 1 to 2 kilometer ocean, covering the similar period initially, and also exploring can we get a carbon cycle in there. And so, yeah, that's kind of the things I wanted to describe. This is my summary. So just want to remind everybody, 100 years ago, L.F. Richardson was talking about 1,000-kilometer scale modeling. So there's a picture of Germany at 1,000-kilometer scale grid boxes. We're now at kind of, down to the 1 kilometer thing. And this is from, there you go. That's my 12 minutes up. I will just tell that to be quiet. And then, so we've had understanding planetary dynamics, subgrid scale improvements for kilometer scale course modeling, nature runs and observation testing. These are the kind of main applications we have. Technical challenges, ice coupling. I would say just the complexity, cost, and workflows are leading to mistakes and having to go back and visit things. And then distributing outputs to anyone everywhere, everybody's said. And then initialization. These are the other things. Some other things that would be great to chat with people about while we're here. We've moved some capabilities to the Julia language. Nothing here is using Julia, but we're kind of interested in what the future holds there, and we are doing a bunch of machine learning and Bayes emulators to kind of learn reduced complexity and precision schemes from these sorts of models with a view to saving energy, carbon, and time. That's it.
We have time for a couple of questions.
Ooh.
Fighting. They're fighting over
fighting
it.
for questions. Oh my God. Okay, I'll give quick answers. So not much. We are not doing anything at the moment. We actually have someone who's doing a little Langmuir kind of parameterization scheme that's not in here at the moment. But certainly if you look at the density profiles right near the surface, we probably should be doing something more in there. But
Part 2 is ocean tides.
we do, yes. All of these have tides in them, and that's been a huge advantage for some of the observational work in some sense. It's also a pain, but it's made things.
Interested to know how you do that. And then the third, maybe more useful question is, you've output all these petabytes of data. Have you got any insight of which variables and how many times those are used and so on? Having that kind of analysis of you've been great.
Yeah, I mean we do. I'm not sure that we should take it as kind of people are looking at it in various areas and things. There are a lot of people have been looking at surface processes. I would say that's SE coupling, and that's partly I think just because that's where a lot of the observational missions are going and the things you can see from space, and we do a lot with NASA. So yeah.
I mean, you said you did a longer run as well, so I was just curious, how is your SST in the tropics? Is it too warm, too cold? Is it drifting? Did you look at it?
So we have looked at the tropics. I think, did I say we did a longer run? I didn't think I said that, but maybe I. Yeah, 40, the diamond, yeah, sorry, beyond the diamond. Yeah, so we're starting to look at that. So far, we show, Anish showed an MJO thing. We're kind of looking at the thing. It's really, we've only just started looking carefully, but we're not too scared by it at the moment. It's kind of,
Thank you. Thank you very much. Okay, we'll move on to our next speaker. So this is Sun Xian Lee she's going to tell us about progress towards global cloud permitting greenhouse warming scenarios. I'll give you a 2 minutes.
Hello everyone, I'm Sun Lee from IBS Center for Climate Physics, ICCP, and my talk is on the progress of global cloud permitting greenhouse warming simulations. I would like to thank all collaborators. First of all, I'd like to introduce our main Earth system modeling activities at our center. And in 2019, we conducted a high-resolution greenhouse warming simulation using CSM 1.2.2, and it is century-long 2 times CO2 and 4 times CO2 simulations. The horizontal resolution is 25 kilometers for the atmosphere and 10 kilometers for the ocean. Then we conducted CSM2 large ensemble simulations by collaboration with the CSM group at NCAR, and we also did past 3 million year transient simulations. Of course, these two are not the high resolution simulations. Nowadays, we are working on the global cloud permitting greenhouse warming simulations. So today I show the progress on this project. This new high-resolution simulation project will be done by collaboration between ICCP in South Korea and ABI in Germany. The research goals are to resolve the ocean sub-mesoscale variability and its interaction with the atmosphere, and to understand the multi-scale convective system and its connection to the large-scale environment, and to project long-term future climate in local and regional scales. For this project, we are using the ABI CM3 model, which is recently developed, and stripping error shows that this ABI CM3 model shows higher scale in representing observed climatology, and it also shows good computational efficiency. The ABI CM3 is composed of open IFS atmosphere model and PHASM2 ocean model. This is the planned experimental design, and this summer we finished fine-tuning of TCO 319 DART configuration, and the horizontal resolution in TCO 319 is about 31 kilometers in the atmosphere, and there are 137 vertical layers. And for DART mesh, the horizontal resolution is 4 to 10 kilometers in the Arctic and Southern Ocean, and there are 80 vertical layers. This figure shows DART mesh resolutions, and it has about 3 million surface nodes. And this configuration is also used our production runs. Based on this configuration test, we recently finished 50-year spin-up simulations, and then we will do the transient simulation from 1950 to 2100 and 1950 control simulations. And also we plan to do several short snapshot simulations with very high resolutions. For these planned simulations, we are using the IBS ICCP supercomputer Aleph, and Aleph peak performance is about 1.43 petaflops, and there are 468 computing nodes, and we are using 85% of total. The RBCM3 TCO 319 Dart configuration SYPD is about 6.5 to 7 on 350 nodes. Now I show the main result from the fine-tuning, the TCO 319 Dart configurations. This is the SST variability, and the interannual standard deviation of SST in each season shows reasonable variability, and in general, except for the tropics in spring and high latitude and Arctic in summer. We also examine the ENSO variability to assess the model capability in representing the climate variability. And NINO 3.4 times reads in observation, and model is shown here. And RBCM3 can reproduce the ENSO variability, internal ENSO variability well. And also ENSO phase tracking is well captured in the models. And El Nino and La Nina Hobomolo composite indicates that the model can capture the overall observed SST evolutions. Next one is tropical cyclones. Comparison of model with observation suggests that the RBCM3 can capture the major tropical cyclone genesis locations, tracks, and density. But still, there are some biases over like this and high latitude like this. And in terms of tropical cyclone frequency, we found an overestimation in the Eastern Pacific and South India and Western Pacific. But the model performance in North Atlantic and North India and South Pacific is really good. This is the sea ice extent in the northern hemisphere result. And model underestimate annual mean sea ice extent like this, but it simulates where the interannual variability in the spring and winter sea ice variability. And also the model simulate a little bit strong annual cycle than the observations. In the southern hemisphere, the annual mean is a little bit weak compared to the observation, but the interannual variability is a little bit strong in the model. But we think the model can simulate overall the features of the sea ice extent. And today I didn't show all results from our fine-tuning result, but the model performance for the other fields, including the QBO, precipitation, and wind, AMO is also good. So we decided to close the tuning, and this version became the basis of our production runs. This is the last one, and our future plan. As I mentioned, we will do the this year we will do the transient simulation from 1950 to 2100, and we will do the 1950 control simulations. And in 2023 and 2024, we plan to do the several snapshot simulations with 9 kilometer and 5 kilometer atmospheric resolutions. And in these snapshot simulations, we also apply the higher resolution of Bezel. That's all. Thank you.
Very much. We have time for a couple of questions.
Yeah, you showed various aspects. Tropical cyclone behavior is something similar to the previous Nikan behavior. Yeah, we think bias, particularly Central Pacific and very few Atlantic hurricanes. So from this point, we struggle to trying to improve models. So what's your strategy to improve this model?
My colleague is, for the tracking scheme, my colleague used the OWGP scheme. It called OWGP and Okubo, why something like that. I don't remember the exact name, but maybe we need to modify that scheme for the better tracking.
Which scheme you are most interested in? Scheme. What kind of scheme did you say?
It calls OWZP scheme. Yeah. I don't remember the full name. I don't. Yeah. Some kind of Okubo-wise zeta parameterization, something like that.
Staying in the topic of tropical cyclones, what you don't show in the annual cycles on the right is actually the South Atlantic, where in the model there's a bunch of tropical cyclones.
Right.
In the observations there are none. I'm wondering if you have any speculation why that is, and I'm also asking if we see that in other models too.
I don't know the.
Not good.
Yeah, so I was also going to ask about the tropical cyclones actually, because your model, have you already done runs with higher horizontal resolution? So this was 30 all these results were 30 kilometers, and I'm kind of fascinated because we saw Steve Yeager's talk earlier, and that was 25 or something atmospheric resolution, right? And that was also an overestimate of the number. You only had the total number, so we don't know what the distribution in the basins is. And so I'm kind of fascinated that a 25-kilometer model should do that, because it shouldn't be that great at doing tropical cyclones, and it still has parameterized convection, which we've been saying all week is bad. So it would be. Do you have any insight as to why it happens yet? Do you have any idea why? Is it just the tracking scheme and just a diagnostic problem, or is it a model thing?
I don't know. We didn't try the higher resolution yet, but we needed to look at that. Yeah.
I was just going to make a comment following what Christian was saying, because we just saw another plot today of tropical cyclones, and if you paid attention, I suspect what you're showing there with the colors is some metric of intensity, those green to yellow colors on the tracks.
No, there is no intensity.
What are the colors on the tracks?
Just a
number. It's just a number. I can't see.
Yeah, just the tracks.
No, but you're plotting all the tracks, and they're colored.
Oh, there is no.
And then there is a legend at the bottom.
The bottom is the topography. Sorry.
No. On the track, each track.
Each track has the same color.
Topography.
Yeah.
On the tracks.
The track is the old thinker.
Ah, okay, okay.
Yeah.
What is the color on the tracks?
The yellow is genesis locations, and bluish is just track, not the intensity.
Okay, all right. All right.
Yeah.
Okay,
Yellow
all right.
that is. Yeah.
Okay, because we saw another plot where I thought maybe the color was the intensity, but at equivalent resolution, the intensity was mostly mid-latitudes. And here comes the question. We need to be able to sort out what's the model and what's the tracking algorithm. So we need to apply a number of tracking algorithms to these things so that we can separate the two.
Yeah, I wanted to make a quick comment, which is along those lines. Why do you see that many tropical cyclones? Because you have a tracker that's tuned to find them. But I assure you, a lot of those are not tropical cyclones.
Right.
The tracker is picking them up for whatever reason, but if you look at them, they're not tropical cyclones.
May include extratropical storms or something like that.
Thank you.
Thank you
very much. Okay, we better move on. So now Robert Untitled is going to talk to us about the large-scale atmospheric circulation response to Gulf Stream.
Hello, everyone. I'm Robert England Wills. I'm a research scientist at the University of Washington, but currently a long-term visitor here in NCAR. And wanted to give you a little bit of motivation for the work I'm going to present today, because I'm a large-scale dynamicist by training, so a little bit foreign to this community. And I also have worked a lot on decadal climate variability. So it's kind of topics that we've heard a little bit about from Steve Yeager earlier, but are a little bit outside the realm of this community. But I want to share how I got interested in high-resolution processes, which is this on the left is showing some nice work by Isla Simpson that shows that reanalysis has more decadal variability in the atmospheric circulation over the North Atlantic than does a low-resolution model. This is the CSM large ensemble that it's comparing to. And if you look at it in observations, the relationship with SST, you can find an associated SST pattern. And so it appears there's some decadal variability in the atmosphere that might be linked to the decadal variations in the SST. And this is exciting because we can do a pretty good job, as Steve was showing, of predicting the SSTs on decadal timescales. So if it has this big impact on the atmosphere, then it might be more valuable for predictions over Europe, for example. So one hypothesis for this is that it could have to do with resolution. And so there's been this canonical understanding for a long time from the climate dynamics community that the SSTs in mid-latitudes don't have a big impact on the large-scale circulation. So this is citing a review paper from 2002. However, there's been some more recent work that show that there is a much larger response at higher resolution. And I'm showing in particular results from this Smirnov et al. 2015 paper where they put an SST anomaly in the Kuroshio-Oishio extension region and looking at the response at a 1/4 degree resolution versus 1 degree resolution in the upper troposphere, Z200. You see this much bigger response at the higher resolution. But there's been fairly limited studies that do this kind of idealized test of what is the impact of the SSTs on the atmosphere at different resolutions. Here's just another bit of motivation showing some regional modeling work showing that the ascent in the warm sector of cyclones is greater in a 12-kilometer model than that 40-kilometer model, looking at ascent over Gulf Stream SST anomalies. So with that as motivation, well, one more slide of sort of motivation, which is that, so a lot of the existing high-resolution work that has gone to decade and longer timescales, for example, the IHASP work that Steve talked about, or also the high-resolution model intercomparison project, has all kind of topped out at a 1/4 degree or 28-kilometer resolution. And so the regional modeling work I showed on the last slide showed a big difference between 12-kilometer and 40-kilometer. So if we push past this 28-kilometer mark, do we get a bigger response? So I'm taking advantage of the variable resolution capabilities within CAM SE and
together with my collaborators, have developed a grid to focus on what is the atmospheric response to North Atlantic SST anomalies. So it has 14-kilometer resolution in this refined region in the North Atlantic. And just also wanted to give a shout out to the great work that's been done with KMSE with a bunch of different other grids focused on continental US or Arctic, for example. So what I hope to do here is to then evaluate what is the difference in the mid-latitude atmospheric variability and the ocean to atmosphere feedbacks across different resolutions, going from this higher resolution 14 degree up to the more CMIP class 110 kilometers. And understand if and how the mesoscale frontal processes are influencing the larger scales. And then if there is a big impact of resolution, I want to determine what resolution we need in order to get skillful atmospheric predictions from what's going on with the SSTs. So to do this, I'm looking at some pretty idealized experiments within this grid where, as a reference simulation, I have climatological seasonally varying SSTs. I'll note that the SSTs I'm imposing are at 1 degree resolution. So unlike Steve's work that showed really the importance of this, the ocean mesoscale eddies, this is just looking at the role of atmospheric resolution. Then as an anomaly experiment, I'm looking at an SST anomaly pattern with a strengthened SST gradient across the Gulf Stream, so warm SSTs in the south and cold SSTs in the north. And just comparing the difference between these two simulations at both the higher resolution 14 kilometer atmosphere, sorry, and then the lower resolution 1 degree atmosphere. And just wanted to put up the cost of these simulations. It's because I have this variable resolution and it's only 1 degree at the far field, it is pretty cheap by the standards of this conference, only taking about 70,000 core hours per model year, which is about 35 times the cost of a CMIP class model for the atmosphere component of a CMIP class model. I do also have an intermediate 28-kilometer grid with the same kind of domain, but don't have results to show from that today. So just going to take you through a bunch of different fields where I'm showing the difference between the SST anomaly experiment and the climatological SST experiment for these two different grids. And in this first result, you can see that the latent heat fluxes on the southern boundary of this SST patch are intensified in the high resolution. Chris Smith maybe gave us another mechanism for that. I've been thinking it's mostly warm sector processes. The cold sector processes in the cyclones might play a role too. Haven't quite gotten to diagnosing that aspect of it. But then there's perhaps even a bigger influence once you get away from the surface. If you look at the precipitation response, everything I'm showing here is DJF averages. You have this more than 2 millimeter per day precipitation response to this 2 degree SST forcing at the southern edge of the forcing region. And that's a factor of about 3 bigger than you get in the lower resolution case. And that continues up into the free troposphere, and you see that there's still a big difference in the vertical motions as you get up to 500 hectopascals, where then this is going to have an influence on the large-scale circulation. So then I think one of the most, one more figure of this is showing then kind of what the cross-section of this, looking across the, at a latitude versus height cross-section, looking across this forcing region, and you can see that there's a, that's not working. That's okay. So you can see that there's this ascent at the further south portion of the forcing region that goes up higher and a stronger magnitude in the variable resolution case on top, versus the flow goes a bit more meridionally on the bottom. And so this changes what the vertical temperature profile you get in the anomaly compared to the reference, and this is part of what's underlying these large-scale circulation differences, which I actually haven't shown yet, but this is what's shown on the next slide. So I think this is the most interesting result, is that then with the large-scale circulation, you get a very different response of the large-scale circulation to these SST anomalies in these two different grids. And the variable resolution case, which is now on the left, is showing a much bigger and also different spatial structure of response to this SST anomaly. You get an Arctic oscillation-like response that has a statistically significant impact in these 10+ year simulations on the North Pacific as well, which is pretty interesting. It seems to be some more zonally uniform aspect of this response, versus in the lower resolution 1 degree case, you get this high pressure anomaly in response to this SST forcing that's pretty confined to the North Atlantic and not much going on outside the North Atlantic. This is a bit work in progress, but I wanted to see how this response projects onto the modes of low-frequency variability. So this is just doing an EOF analysis on 5-day averages across all of the simulations. And so the first one is for the NAO, basically, and looking at how the distribution of the principal components varies between different simulations. One of the main takeaways from this so far has been that even with 10 years of simulation, internal variability is really hard to get around, and you can't really be super confident in your results yet. So I'm running these out further as we speak, but there are some potentially interesting things focused just on the UF1 case on the left, where the orange line, the SST anomaly experiment in the high resolution, shows a wider distribution than in the reference case. So this is perhaps saying it's not just a shift towards one phase of the NAO, it's a widening of the distribution due to the latent heating helping it stick in one regime or the other. This is potentially some evidence of some regime-like behavior going on in the 14-kilometer case, which requires some further work. Then I think in order to get at the mechanisms of why you have this enhanced precipitation, what really is the underlying mechanism, why the resolving the atmospheric mesoscale matters, I think it's important to then do some Lagrangian tracking and look at the processes. Where is this extra ascent happening within the cyclone? I haven't done that. I wish I had that to show you here today, so I'm just showing here basically some eye candy of, maybe not by this conference's standards of high resolution stuff, but a bit what these cyclones look like in the variable high resolution case with the SST anomaly. You can see some interesting things already just watching these cyclones progress, where there is lots of rainout as it hits the SST anomaly, which is shown in these dotted lines, or some of the cyclones tend to really shift and follow the SST strip that you have along the bottom. So it seems to be influencing even individual cyclones, but I haven't quantitatively analyzed this yet. So in conclusion, the 14-kilometer regional refinement shows an increased large-scale circulation response to Gulf Stream SST anomalies compared to a more CMIP class resolution. And the warm SST anomalies in the southern part of the Gulf Stream are causing some mesoscale ascent, which then impacts the free tropospheric temperatures and leads to jet shifts. And so still some work to understand what are the mesoscale mechanisms here that are leading to this increased ascent, to see if you really do need this 14-kilometer resolution or if 28 kilometers might be enough. And also, Isla Simpson, a collaborator here at NCAR, is running a full AMIP simulation with this grid forced by 10th of degree SSTs. So we're excited also to look at the interactions between the atmosphere and oceanic mesoscale using the simulation. So thanks, looking forward to questions.
Thanks very much. We have time for a few questions. Question.
So presumably the 14K still has cumulus parametrization. You didn't change any of the physics as you change the resolution?
Yes, there's definitely, I think with 14K we're safely in needing a convective parameterization regime.
Well,
and that's kind of what limits us from thinking about going to even higher resolution, is because then that would require thinking about turning the convective parameterization off.
It just sort of means you probably have to investigate this a little more, but with the sort of suspicion that cumulus parameterization schemes tend to be a bit too surface responsive. So if you put a big SST anomaly there, they may do things that resolved convection won't do, but it's difficult to know. I just wanted to know. Yeah, it's very cool though, actually.
Any other questions?
Maybe I didn't get it right, but do I understand it right that the ocean is not interactive, right?
Yeah, it's a specified SST, so the SST can't change, yeah.
Do you think that the response can change if you have an interactive ocean somehow?
Yeah, absolutely. I think this is trying to cleanly isolate what is the atmospheric resolution piece of this, and but then the next step would be going to coupling this with an ocean.
Yeah, I'll be interested to see your results from the 10th of a degree, because you may see some sensitivity to just giving it higher resolved SSTs, certainly. So.
I think it's already in the late 60s, so we have about 10 years of that, but no analysis has been done yet.
Okay, thank you very much. Okay, so now we have Olivier Geoffroy, and he's going to talk to us about global kilometer scale atmospheric model centennial scale simulations.
be by Michael Haller, and he will show the added value of convection permitting climate simulations over Germany.
Yeah, hello and good afternoon. I will report today about the activities of the DWD, the Deutscher Wetterdienst in Germany, in the field of regional convection permitting climate simulations. And I will show some results about our analysis of added value. So at the DWD, we use the regional climate model Cosmos CLM here in the version 5. So we performed convection permitting climate simulations, which are centered over Central Europe. So you see here on the right side the model domain. So it's centered over Central Europe with a 3-kilometer grid. And the configuration was taken from the activities of the CLM community in the FPS convection, which was also already topic here. So we have basically the shallow convection parameterization and prognostic Doppel and so on. So we performed several runs. The projections were driven by the GCM Marek 5. For that, we used the intermediate nest on 12 kilometers. And we have, for the projections, 3 30-year time slices, 1 for the historical and 2 for the future. So for the near future and the far future with this RCP 8.5 scenario. We had performed an additional evaluation run, which was driven by ERA 40 and ERA 5. And there we have basically around 50 years of simulation and until 2019, and now the last 2 years also in preparation. There we just restarted the model. And this run will be quasi-operational extended. That means as soon as ERA 5 is available in the data archive, then we restart the model, and yeah. We have hourly output, and for the main variables and for precipitation, we have even 5-minute data. For our analysis, we use different data sets, and here I show comparisons with the Radklim. This is a gridded radar observation data set for Germany. It's calibrated with station gauges, and it has a horizontal resolution of 1 kilometer. So just a bit of advertisement. The projections and also the evaluation run are now available on the ESGF. So if you're interested, you just can download it there. Now I come to some results. This is here for the wind. This is just the 30-year time slices for the historical and 2 future time series. And what we just wanted to know is if these time series differ and if the difference is significant. And so we made a test. We made a test with a man-made U test, and so we found out that indeed we have indeed a significant difference between the historical and the far future. And you can see it here already by eye, more or less, here in this plot. And what is basically happened is more clear here in the PDFs. So we see here that for the wind speed, we have more lower winds and less higher winds. And this holds also for the wind gusts. This is this parameter here. So this is more or less the same here. Then we wanted to know where that comes from. So we looked at the annual cycle. And we also divided the area of Germany into 3 different regions and looked if how it looks like over the annual cycle. And what is seen here that we have basically more or less in all months a decrease of the wind speed, but it's most pronounced here in spring. It holds for the wind as well as for the wind gusts. So our guess right now is that maybe come from the GCM itself, but there's still some work to do, and we will have a closer look at that, if that's true, or if there's another reason for that. Okay, now I come to the precipitation. So there we looked at the Diurnal Cycle. This is here in comparison to era 5. And for the domain of Germany for 16 years. Again, the reference is Radklim. And this is very similar to what Nicolina also already showed on Monday. So we have here a quite good correspondence between Cosmos CLM and Radklim, but except this nighttime precipitation, there Cosmos CLM is too high. But when we compare to era 5, we see that there's a big overestimation over the day. And we wanted to know if there's a difference between different regions. So we divided Germany in 12 regions here. This is shown here. And what we can see is that especially for upland regions like the region 3, 1, 8, and 9. Yeah, 1, 8, 8, and 9. There we have an overestimation of the precipitation at Cosmos CLM. While for era 5, you see that this overestimation during the day is basically in all the regions, so this makes no difference. At the other hours of the day, we see that it's a bit similar to what Cosmos CLM shows, so yeah. Then we looked at the precipitation intensity and the wet hours over the day, and there we see that Cosmos CLM has quite good performance. We see a small shift, so the peak over the day is earlier than in Radklim. We see also a Diurnal cycle in era 5, but the intensity is overall too low. For the wet hours, we see again a quite good correspondence of Cosmos CLM to the reference, and two high numbers of era 5 here, especially again over the day. Now then we applied the peak over threshold method and looked to extreme precipitation, and this is here now for daily precipitation, 24 hours, and a return period of 30 years. And again here on the left side the Radklim data set, and in the middle the model results. And what we see here is that for northern Germany, we could say, okay, this is quite okay, but when we look at the southern part of Germany, we see here a strong overestimation, 30 to 50%. If we look here, this is just a difference between model and observation. Then we looked at even shorter durations. This is here now for 3 hours and for 1 hour. Again, the return period of 30 years. Please mind the scale. So the scale is different, and you see from here that the model has too much precipitation. And what is also seen here is that the orographic patterns, so we have here the Alps and here in the middle some upland regions. This is disappearing here in the observations, but in the model it's still visible. It's just only a bit weakening, but it's still there. So we see here that the model is still showing an overestimation of the orography in terms of extreme precipitation. Now, say some words about the activities of the CLM community. So we contributed to the Cortex FPS convection with several Cosmos CLM runs, and so this is a part of the first convection permitting climate model Ensemble, which is introduced by Coppola et al. A big issue now is also the transition to a new model. So we have we go over to the ICON CLM. This is just a development of the regional climate mode of the ICON by the CLM community. And the model is now in a stage that is already applied, first by the project Nucleus, but so far only for 12 kilometers for Eurocortex simulations. So there are also some more activities planned for CMIP6, but we also need first some tuning experiments to find the recommended settings. This is done in the COPAT, so-called COPAT 2. This is coordinated parameter testing. And this is done quasi-parallel to tuning of the last official Cosmos CLM 6 version. So this is more or less done parallel. And when this is done, then we can go the next step towards the convection permitting scale again for ICON CLM. Okay, now I come to conclusions. So we made Cosmos CLM simulations with 3 kilometer grid for 30-year periods. They are summarized and, as I said, published on ESGF. We are now also in preparation of a 3-step scheme for quality check and evaluation of our simulations. We have seen for precipitation that we see an added value in comparison to coarse renaissance data, but we still also see very strong overestimation of extreme precipitation for wind gusts, for wind and wind gusts. Yeah, we have just started our analysis. There's still some more work to do. And as I said, we are now going towards the ICON CLM, but right now on the 12 kilometer scale. Okay, thanks.
Thank you. Are there any questions?
Yes, nice talk. Did you look at how the bias was changed from your 12 to your 3 kilometer GCM downscaled runs?
You mean from the 12 to, from the GCM to the RCM?
Yeah, I thought you mentioned you downscaled MyRock 5.
Yeah, yeah.
And you downscaled it onto a 12 and a 3 kilometer grid?
With the intermediate nest, yeah, right, yeah, yeah.
And did you look at how that did you look at the bias on the 12 kilometer grid?
Not really, no. Well, we had this MyRock 5 12 kilometer run is also in our climate model Ensemble, and this was bias corrected and downscaled to 5 kilometers. So there was also look at the bias, but I cannot say now more about that. But
and you bias corrected prior to downscaling, huh?
This was another project, or it was another work by a colleague from me. He made first the bias correction, then downscaled to 5 kilometer. Yeah.
Okay, thank you.
Okay, thank you. Let's move to the last talk for today's session by Michael Eck. I thought it would be on the land, but I'm a bit puzzled by the title. So the floor is yours. I was expecting land, but...
You would have expected land, that's right. I'm always typecast in that. So anyway, a lot of authors here, and Jimmy, I probably forgot to add you. It's a combination of people at NCAR as well as the Global Systems Lab for NOAA here in town, and the Developmental Testbed Center, which we're all a part of. So title of this is Improving Earth System Modeling via Hierarchical System Development, and we'll talk about what that is. I mean, we all should recognize that. So let's see, forward. Here we go. So Earth system model development process. Well, there's a lot of resources and a lot of things. Is this the previous or the current paradigm? Think of all the literature that you have out there that we publish. There's a lot of great research that has gone on, and that needs to be transitioned somehow into the models. And so what is the process? Well, I come from an operational community previously, as Fanglin knows. Is it toss it over the fence? Well, how do we improve this process, really? So what is a hierarchical system development? Well, from a taxonomy of the word, basically an arrangement or classification of things, hierarchical system development is really a systematic approach. You might call it an engineering approach, where we test small parts or elements of the model, like a physics scheme and so on, of an Earth system model in isolation, then progressively connect these things up with increased coupling between all of these, all the way to a fully coupled model. System really implies that it's end-to-end, data ingestion, quality control, data assimilation, modeling, post-processing, verification. So, and then actually to do this hierarchical system development, you really need an infrastructure that connects these steps somehow effectively, because you can do a lot of things individually, just focus on a process, etc. And if you have an infrastructure, it makes it work even more efficiently. So why do we need this hierarchical system development? Well, to understand systematic model biases, we start by simplifying the Earth or atmosphere down to a few key processes and focusing on those. It's for efficient use of computer resources as well, and to fix bugs and so on before you make really long runs. You want to fix a little thing as opposed to, well, let's just run it for a season and see, how does that look? Well, you want to actually test those smaller parts before you commit to doing those longer runs. There's many Earth system processes that we need to consider, from local processes here, and this, let's see, does this work? Yeah, well, sort of. This is simplified in a sense. Local processes all the way to fully global processes. So there's a lot of territory in between, and we need to improve those. So just a little background, there was a nice climate workshop in 2016 to look at hierarchical approach to understand model components and their behavior. And there was just a recent follow-up hierarchies workshop in Stanford at the end of August, early September this year. So they were addressing these kind of issues. And I like some quotes from the original workshop in 2016. Tim Palmer said, "Hierarchical thinking should be second nature for all weather and climate scientists." Of course, I really like that quote. Julia Slingo, in her 2017 review of WCRP, said we need an increased focus on making sure we have that process level understanding in our models, and we need to connect weather and climate. WWRP, WCRP, those are just different sides of the same coin. Christian Jakob, who couldn't be here, basically had a really nice paper in BAMS in 2010. The community needs to improve the diagnosis of processes contributing to model errors, and we need more developers, not just users, but developers of models. So we really need to understand all this dirty laundry. This talk is mostly conceptual, but I have a few examples here. But anyway, we need more model developers. So we followed his paper a bit and wrote a hierarchical system development focused article for the NOAA Unified Forecast System, but it's equally applicable to other models. This is just a link to it. And there was a nice little schematic that we borrowed from Christian, expanded here. Unified Forecast System, just call it for NOAA. But what's interesting is you have this development cycle where you run the model for a number of maybe different time scales and so on, but then you assess a particular application, regional, global, etc. And so you calibrate the system, and you can actually make the model come up with good results, but you have limited insight into the behavior of those processes in the model. On the other hand, where maybe a a lot of the research goes on improving the processes, you have the cycles down here, which you have very focused studies on what we can do to improve a particular process. And you can learn about a lot about the process, but you learn less about the system. But you can actually connect these steps with a big cycle and these little cycles as well. So making sure that what's going on in this fully coupled model, and then making sure you can learn some things from those process level studies. And so ultimately those things fit together. Now I came up with another schematic, a simple to more complex, comprehensive approach to identifying biases and improving models. So if you start with a single process, just talk about the surface layer and wind profiles, temperature profiles, etc., a single process, all the way to a complex system with many, many, many different processes going on. There's two things you can do. You can learn about the processes so that you can understand a lot about the processes if you just focus on a single process or a few. And here's the example of a lot of processes that are local. And you can, your understanding of the system, of course, when you look at the entire system, you understand the system. But you can't learn a lot necessarily about the individual processes. So there's a continuum. And so we propose this kind of testing harness where you can focus on just individual process simulators like this process over here. Looking at single column models, as Christian was talking about, hey, we can learn some things from there, necessary but not sufficient, of course. A friend of mine said, hey, you need 2D models in here. Okay, I'll add that. There might be a small domain model that you just focus on a small area, look at the convection. How is that behaving in this controlled area? But you don't have to run the entire global model or regional model to help you learn some things. Then, of course, there's regional models, global models as well, and then fully coupled models. Now, it's important that you assess at the process level what is going on in the single simulators, in the column model, all the way down to the fully coupled model. Am I getting the surface fluxes right? Okay, and you can see those throughout this hierarchy. Now, of course, you can't learn a whole lot about the 500 millibar height anomaly correlation score by just looking at an individual process. But I contend that you really need to make sure that you look at the process level at each of these steps. You can drive each of these components or parts of this harness using observational data, model output, idealized data, just to get a better picture in fully understanding the behavior of what's going on. And of course, the regional, global, fully coupled model can be cold starts or cycled, including DA, et cetera. And really the simplest thing to look at is the single column model, which I will say right now we're working on just taking our single column model and just having on-off switches for all the physics. So you can just focus on one process. Then, of course, you have to have the driving data to focus on radiation, boundary layer, and a number of things. 2D is a future capability. So this is kind of the conceptual thing that we're trying to do. So here's just a couple of process level examples. Let's not read all this. Basically just, hey, let's focus on the canopy conductance. So this is a piece of the surface moisture flux. So it's a subcomponent. So there's a lot of steps you can do to identify just what are we going to do to improve that. Same thing for the surface layer exchange. There's some things that we can do to understand the process that's going into the surface heat flux. The surface layer exchange coefficient is simply a subcomponent of the surface heat flux. You can move on and focus on trying to understand the land model and focus on the surface fluxes. So there's a number of factors that go into calculating those, but then you can come up with a systematic evaluation. This happens to be different times of the season and different surface energy components. So there's a focus. And then, of course, you can look at single column model studies and focusing on land-atmosphere interaction, ocean-atmosphere interaction as well. But it's important to point out that these are just single hierarchical system development process level focused studies, and they're not connected. Well, what do I mean by connected? Well, let's step through that. How do you connect all these processes in an efficient way? What we have that we've been working on at NCAR and in the Developmental Testbed Center is this Common Community Physics package. What is that? And so we're using that for testing physics in these various modeling systems, or this hierarchy, this testing harness. Basically, the Common Community Physics package is a library of physical parameterizations, 2 minutes, I will hurry, and an infrastructure to connect all these parts. CCPP lowers the bar for the community to test their physics, because once it's in here, it's in the model, it can be used in the single column model and so on, individual parameterizations, regional, limited area, etc. I'm jumping all over the place. So the CCPP provides this software infrastructure so you can enable all these different hierarchical system development steps. Just talking about it, it's being used by NOAA, Naval Research Lab, NCAR, etc. So just here's an example, and maybe I'll just go through one. So physics and evaluation for this unified forecast system. Here's just the output. So we're looking at the global forecast system, which has cumulus, PBL, surface layer physics, etc. We identified a bias partitioning between liquid water and ice, and that gave you a biased radiation at the surface, so biased liquid cloud and ice water path. So what we did is we used this hierarchical system development approach, just focusing on use of the single column model to identify what's really going on. And so we were comparing the single column model, the LASSO LES output data from the Southern Great Plains, and compared it with the GFS. And by doing that, looking at it in two different ways, we pinpointed the key processes that were leading to the weak radiation inversion. You may not actually do that by just looking at the fully coupled model, but certainly you can address, or you can identify the key areas that were going on. And in this case, there was, well, I could kind of walk through those. The key processes that were leading to weak radiation inversion: strong entrainment, the capping inversion had excess clouds, lower wind levels, stronger entrainment, not enough, and not warm enough surface, and then a weak nocturnal inversion. So I guess since I have less than a minute, there was another example that we were looking at, this spatial dependency, 3, 13, 25 kilometers. And basically our takeaway was the physics suites did not produce scale invariant results, which we're really after. We want to understand those connections. I'll jump by this one. This is from the MUMIP project for WWRP. Again, coarse resolution, fine resolution, trying to understand those. So, summary and challenges. Earth system models for weather and climate are getting more and more complex. We need to get the right answers for the right reasons. How? Well, this hierarchical system development is this engineering, systematic engineering approach, so we can look at those small pieces and go all the way up to fully coupled models. Common Community Physics package for us is a very efficient use of that. But wait, so all of this, how does all this apply to our ultra-high resolution climate modeling? This hierarchical system development can help you understand the improve the understanding of spatial and temporal dependencies in the model physics. And we really would like to have consistent solutions between these model resolutions, including all the way down to the kilometer scale. Thank you.
First, thank Michael. We have used a lot of the single column model on the CCPP for NWS forecast model development. Question have the single column model. How we in the past 3 days we have seen a lot of the simulations or forecasts as highly resolution dependent.
Yeah.
We have a way to use the single column model capture the horizontal dependence or model resolution dependence.
Oh, you mean like in vective terms?
Like they showed earlier today, if the ocean has a much higher resolution, even the latent heat flux is different.
Short answer, yes. but I think we would really be delving into a lot of the various parts of the hierarchy that you really need to investigate. And it's important to understand you can learn some things from the single column model, and I think it's a necessary condition, but not sufficient in your model development. You really have to cross all these thresholds and look at the model in all these different ways. Is this really a large task? Absolutely. The Common Community Physics package is nice because once it's in there, then we can look at all of these different parts of this harness, if you will, to be able to address just what you were talking about.
Okay, then thank you. Let's thank all the speakers from this afternoon. And we'll reconvene tomorrow at 9 with some talks on the technical side. Have a nice evening.